Kasia, możesz już
szerować?
Okay, let me just double check. Can you please close the door? Just double check if everything works fine. Right. We are online and we are on Zoom, so welcome everyone and welcome to the third day of the 12th Gaia Science Alerts workshop and the first ORP time domain workshop here in Heraklion in Crete, in the Forbes Institute of Astronomy. We are gathered in this room. You can see us here, and speakers are some talks will be given from here, some talks will be given from Zoom. And without a further delay, I'll give the floor to Monika Sitek, who will be chairing the session today.
Okay, hello. We will start today with Katarzyna Kruszyńska lecture. Her subject is highlights of photometric microlensing with Gaia Science Alerts. So please, Kasia, you have 15 minutes with questions.
Okay. Hello, everyone. As Monika said, my name is Katarzyna Kruszyńska. I'm a PhD student at the University of Warsaw, and my supervisor is Łukasz Rzykowski. Today I will be talking about the microlensing highlands, the microlensing events that we have found in Gaia. First of all, since I'm the first person talking about microlensing extensively, I would like to introduce you to the concept of microlensing. It occurs when a massive object passes in front of a star within our galaxy or its neighborhood, and this causes a distinct change in the light curve, as you can see on the left-hand side. Because the image of the source is unequally brightened and split into two images, it also causes a shift of the centroid of light, and this can be observed as astrometric microlensing. Gaia has capabilities to observe both of them, and Chris Rybicki will be talking later today about astrometric microlensing observed by Gaia. Gravitational microlensing has been a concept which has been known for a long time. However, it has been reintroduced in the 1980s by Bogdan Baczyński. He has suggested to use it to verify whether or not machos really exist. What's going on? Machos are machos were supposed to be these compact dark objects which were supposed to live in the halo of our galaxy, and Bogdan Baczyński suggested to observe for an extended period of time the Magellanic Clouds, and if machos really exist, we will see multiple microlensing events caused by them. Eventually, the machos theory have been disapproved. However, the concept introduced by Bogdan Baczyński has kickstarted several microlensing surveys, such as Macho, Oval, and Eros, and later on MOA and KMT-net. By the beginning of 2010s, the theory of machos has been thoroughly disapproved by Oval survey. However, by this time, microlensing has proved itself to be a very useful tool for other users. And first of all, it is an amazing tool to observe exoplanets, especially called Neptunes, for which other methods are insensitive. And this is the reason why Nancy Gray Roman telescope will focus for a long time on observing microlensing events in bulge, and it is going to provide hundreds of such planets once the telescope is launched. Secondly, since we don't really need the lens doesn't really need to produce any light, we can try to look for dark remnants of stellar evolutions such as black holes, neutron stars, or white dwarfs. And finally, if we have a lot of microlensing events, we can use them to study the structure of galaxies. Since 2016, Gaia has observed many microlensing events, and this is the map showing all of the events that we have found until yesterday in Gaia Science Alerts. As you can see, it's over more than 400, which is a very nice result in my opinion. And here are some highlights. And as you can see, Gaia sampling is very low, which means that the light curves are very patchy, and we have a high chance of missing interesting or important features of the light curve. That's why we rely and we cooperate with many ground-based observatories. Such many of them are within the ORP networks, but not all of them. And for example, we cooperate with CO, SmartRAM, Loiano Observatory, Aristarchos, OHP in Provence, and Moletai in Lithuania. And Łukasz Wyżykowski already talked about it on Monday. Secondly, for most interesting or most suspicious events, we do spectroscopic follow-up with multiple different tools, such as ISOX shooter, VLTX shooter, LT Sprat, SALT, LBT, Gemini, and Shamaki Observatory in Azerbaijan. And the results of spectroscopic follow-up will be shown in the upcoming paper written by Paweł Zieliński. Lastly, we also use photometric classification relying on archival data. And results of this method and how it is done will be explained in an upcoming paper by Ilknur Gezer. These are the same light curves, but now with two additional events, but now with follow-up. And as you can see, many of the gaps have been filled by ground-based observatories, and without them, it would be very hard to obtain a correct microlensing model. I would like to point your attention to Gaia 19 BLD in the middle top row, which was observed not only photometrically, but also spectroscopically, and Arnaud Cassan's team has also followed it using Pioneer, and he will be talking about this later today. Secondly, Marius Masculinas will be talking about Gaia 19 DKE, which is a long microlensing event from north. And Gaia 20 FNR is a fairly recent, interesting binary event for which, without follow-up, you wouldn't see this little bundle here. And the last one that I'm showing here is Gaia 21 EFS. It's our latest highlight, and it has passed its peak brightness just about a week ago. These are some spectra that we have gathered over the years. As you can see, we are using different tools. Sometimes we take multiple spectra of the same object, and we are using them for two things. First of all, we want to classify our event, whether or not it's microlensing, maybe it's something else. And second of all, if it's microlensing, then we can obtain distance to the source, which is very important for later analysis and lens distance and mass determination. This is the last highlight of Gaia Science Alerts microlensing events that I would like to talk about. It's Gaia 18 CBF, which has been, for which we have fortunately finished the analysis. It is a very long event, which has lasted for more than for around 1900 days, and its Einstein timescale is longer than 450 days, which makes it actually second longest microlensing event ever observed. It's also very dim, which constrained us in the usage of ground-based observatories, and for this event we only would follow up this event with LCO 2-meter telescope at Sighting Springs Observatory in Australia. This is the, we have, sorry, one moment. I'll check my notes, I got nervous. We have conducted a detailed analysis of the lens, and we have concluded that the lens is most likely a 2 to 3 solar masses object located around 2.5 kiloparsecs from us, and because the lens is a very dim object, it is not likely a main sequence star, and we conclude that it would be a possible dark remnant, maybe a neutron star or a massive object. The results of this analysis have been submitted to astronomy and astrophysics. Finally, Łukasz and Laurent talked a little bit about this. Łukasz, Chris, and I have worked on preparing a catalog of candidate microlensing events found in the Gaia Data Release 3, and this catalog will be published in May 2022. And now I would like to use this occasion for a little reminder for everyone who wants to observe our targets. And there are 3 simple rules. First of all, I would like to, first of all, if you are observing one of the targets, microlensing targets, please be consistent when you use filters. If you choose one set, please stick to it. And since microlensing events tend to be caused by cooler objects, it's not very useful to use blue filters. So instead of ultraviolet or blue filters, opt for red or infrared ones. Secondly, if you started observing the target, please finish observing it after the event has ended, because we need data from blocks during the event and from baseline. Ideally, the greatest light curve, well, maybe that's even too long on the baseline, but ideally, a great light curve would look like here on the bottom panel, and not on the top one. The top one is bad, no, a crying emoji. And finally, once you have your data, once you have done the preliminary reduction, submit it to Black Hole Tom as soon as possible. It's a great tool. I have used it personally for adding a few images for Gaia 18 CBF, and just within maybe 30 minutes, I got science-ready products. So please use it. It's great. It's very, actually much simpler than I anticipated it to use. So I think it should help. And this is the summary of my talk. And I would like to use this opportunity to thank everyone who has contributed with their data to microlensing events. And well, thank you very much. Your data is invaluable, and it makes it is extremely useful. Thank you very much. And that's it. I think I can take questions.
Thank you, Kasia. So, any questions? Okay. Anybody wants to share something with us and ask Kasia?
Everyone is asleep after the
lunch and
trip we
trip.
have to Skinekas.
Exactly.
Are there any questions on chat?
No.
Kasia
is very sad that you don't want to ask her about anything, but I have small questions. You said that it was published in May, so half of year, and how many objects you think there will be?
We know already.
Okay, so you have everything closed right now?
Yes. So so it will be, well, as you can see on this plot, I think that's
the triangles. Okay, there is the number.
It will be exactly 363 events. Yes.
I haven't seen the number. Okay.
Okay, no problem.
So, anybody else have some questions? No? So, thank you, Kasia.
I have a question.
Okay,
this is Josh.
Hello, Josh.
Hi. It was a nice talk. I mean, it was the first time it was said that you should not use a B filter. I have been observing in BVI already for many hundreds of days, 20 FNR. So I mean, I have a nice curve which I will show tomorrow. So, I mean, should I in the future drop the B filter and use an R filter instead?
Yes, yes. For future events, I mean, for brighter events, it's fine, I guess. But I think more useful data will be gained from red and infrared filters instead of.
If I may comment on this, Josh. So the B band, we normally ignore it. Well, we don't encourage people because most of the events are faint and they are red. So they are actually even fainter in B. Yeah. So it means the data we could get in blue bands are of lesser accuracy. However, if the event is bright, like the FNR, this is completely opposite. Here we can actually get good quality photometry even in B bands.
Yes, yes.
And for a proper study, the blue bands are very useful actually, because then we can extract the SD color change of the background source more accurately. So in principle, B band is useful, but we encourage observing in B bands mostly the very brightest events.
Yeah, exactly.
B band about 14.2.
That's fine. Then.
Yes, this is okay. Yeah.
But majority of our events are much dimmer, and then we gain very little information.
Okay, thank you.
Thank you, Josh, for your question. So thank you, Kasia. And now we would like to.
I am sharing already. Okay.
Yes, Marius, can you share your? Okay, we have it. Are you ready?
Yes.
Okay, so Marius, long time scale gravitational microlensing events of Gaia DKE. You have 15 minutes with questions, please.
Okay, thank you. Thank you. So already Katarzyna briefly introduced this event. I will speak more in details about this long event Gaia 19 DKE. And I would like to draw your attention to issues, actually mainly to the source star distance determination.
Marius,
you
cannot, only you have.
Only I have?
Yeah.
Let's
go back and stop sharing.
Sorry, stop sharing.
And select once again another window.
This one? Probably. Okay, let's try this one.
With this one, you will see all of.
Okay, and now I try to
do
slideshow.
Show. Oh,
perfect.
Yes,
okay, thank you, Pavel. Thank you. So actually, this event starts already 2 years and 3 months ago, and alerting day was 2019, August 8, and actually it is one of the nice looking light cover that is affected with perturbations of F, and it is long event, and now it is close already on 31 of October. It was magnitude was 15.39, so already this event already going down and close to the finish. Not yet on the light cover on baseline, but this light cover, but already it is. We can say that it is actually it is finished event. And since the source is bright, so it is a lot of observatories to join to this follow-up. And first follow-up was done 21 days after the first appear in this Gaia alert page, so by Serbian astronomer Goran Demiljanovic, and 21 days after event was announced. And actually, as I mentioned, it is a lot of observatories that joined to this follow-up, even small telescope can participate in this observation. So we collected a lot of data points. So, and here it is this table generated automatically by black hole tone, and it is on the left side. You see the observatories. Actually, not exactly observatories, but with hashtags which was put the data into black hole tone. So it is more than on the right side. You see the data points, and it is you see that more than 10 observatories collected more than 100 data for each observatory. Yeah, so and already we have more than, for this long event that it is continued for more than 2 years now, we have more than 7,000 data points. This well covered event. So actually, but it is in this table that I showed before. It is the photometric follow-up, and the spectroscopic follow-up was done on LBT telescope, which is located in Arizona on Mount Graham. It is a spectrograph. You know his name. You know it's Pepsi, but really it is nothing with famous drink. It is Potsdam polarimetry and spectroscopic instrument. So it is actually the reason, the main for the spectroscopic follow-up. It was to classify the source star, one of it is, and to see from a spectra what it is, if it is if it is on the spectra, from the spectra we can identify the second component visible. But actually in this spectra which take from LBT, so we determined the main parameters, and using these parameters we know that it is G5 type, GM star, and no second component, no nothing. So it means that it is star, it is single. And due to using this data, we can determine the distance of this source star, because it is the source star. It is important to now know its location. And actually, we use this well-known equation, but it is typically relation between observed magnitude, absolute magnitude, extinction. But it is this paths. It is have some. Every one of these paths, it is have some hidden effect. Let's say like this. So MV, it is typically it is observable magnitude, but for us should be clear that it is the single star, not multiple star, not other component. So it is not signs of some variability. Absolute magnitude as well, especially for the GNs, typically it is one magnitude, but it is the middle value. If you look to the HR diagram, you see that it is the like cloud. It is on this location where it is and extinction as well. It is typically we know it's extinction from the spectra, from the model of a spectra. But if you look to the photometry, so typically it is ratio between color and its change to. So on the side accepted some value, but it's actually this means that it is all the clouds. It should be composed on the same size of the grains or components of the same particles that create the interstellar extinction. So good question. It is why we didn't use the Gaia parallaxes. So, and here it is Gaia not measuring the parallaxes, not measuring directly distances. It is Gaia measuring parallaxes. So, of course, now it is recently it is published in catalog by Jones. It is free available in the Visibda database. It is, yes, and it is who familiar. So it is provide the distance for two values. It is one value. It is calculated using only geometric parallaxes. And our it is improved by additional information from photometry. And here it is in your screen, you see what it is, where is my mouse? So it is geometric distance. So it is approximately 9.5 kiloparsecs. But it is disagreement with our determinate value 4.3 kiloparsecs twice. Here it is geophotometric parallaxes. Of course, it is fixed, this value to the smaller distances, but not enough to be sufficient accuracy. So it is in this case we need to find our independent method to be sure maybe it is spectra for some reason was wrong taken from the LBT telescope, or maybe it is not exactly good calculated values or published values. Let's say not calculated, but published values. This is for this particular object for the Bailey Jones catalog. So we applied, since the source it is bright, so we applied to the well-known two-mass photometry, and it is this star, source star. It is errors for J, H, and K band. It is acceptable. So actually, at least we can to calculate extinction. And of course, we can preliminary, since it is well known the position on color magnitude, where it is located, every spectral and luminosity plus star. So according to this, we can simply to check our results. So here on the diagram on the left side of screen, you see the sequence Gn sequence, and it is G5, G8, and K. It is the spectral classes for the Gn sequence star. Here it is with errors. It is actual position by using two-mass color diagram. It is for our event DKA. And using these equations, we can calculate the magnitude of extinction. What it is in K, it is 0.21 magnitude. So if you take it in this ratio between visual magnitude or V magnitude and K magnitude, yes. So it is actually extinction. It was 1.66 magnitude, of course with error. Yes. So using LBT spectra, we determine that extinction it is 1.7. So here it is the perfect agreement. So this means that actually in this equation that I showed before, the calculation, yes. So we can use this correct extinction value checked twice by two independently different methods. And here on this color diagram, here it is the position we call the redenet. So where it is the position, if it is the star, will be visible without extinction. So in errors, here it is, you see that it is probably the closest point. It is with the diagram. It is G5 spectral Gn class. Additionally, to be sure that it is really the single star, so was taken Gemini-Nov telescope was taken a high resolution imager. So it is what it is. Here it is the image. Now our some additional, some multiple, or something in this image we don't show. So this we were sure that we can use this distance determined by this photometric equation, that it is a little bit more than 4 kiloparsecs, and according to this model, so it is a model that provides that the dark lens it is without 1 solar masses. Probability here it is. So that's about this. So where it is located is actually this event. So if it's in our galaxy, if we look to our galaxy from the top, so it's our sun, it is the source star, something here, yes, it is actually in the middle between Sagittarius and Orion arm. And some here it is should be some massive, no, at least not, probably not black hole because of a small mass. And in the sky, if we look to the sky, so we can, it is on the edge, on the constellation Cygnus and Lyra, close to the cluster M56. What it is, this was our event. It's going to the end. It is located in the sky. So summary. So source star it is clear G5G, and distance it is 4.3 kiloparsecs. Extinction 1.7 in V. Dark length mass 1.5 masses of the sun. So and actually this job it is made not only by me but with my team, and actually collaborating with our colleagues from Poland. So thanks to all this Lukasz Wojciechowski and his team. And actually this work is part of a research project Polish-Lithuanian Black Hole Grant and supported by the following grants: the Polish National Science Center and DAINA, and by Research Council of Lithuania grant member. So thanks for all observers of the event Gaia 19 DKE and European Space Mission Gaia. So thank you for your attention.
Thank you. Okay, if you have any questions, please raise your hand on Zoom. Siegfried, if you want to ask, please switch you on. Okay, I don't.
You can read it.
Okay, so I will read it. So Siegfried asked if there are no model yet from Gaia.
For this object.
For this object, of course. So do you have a model or not for Gaia DKE?
For model for the mass determination for the
Microlensing.
Yes.
I think
Yes.
Siegfried asked for that.
yes, we have.
Good. Okay. Siegfried, this answer is suitable for you, or you want to ask something more? Okay. Silence. So yes, it's okay.
Typically, what's the issue? It is, it is Gaia is measuring with big time intervals with Gaia events. So actually here we invested. So why we need the follow-up of ground-based observatories? And of course was lucky, but it was with this bright event. So there's a lot of even small telescopes participated in this.
Yes, even mine in Ostrovik was participating. Yes, the small one. Okay, so thank you one more time. And right now we have a really fast talk. Cornel.
Hi, can you hear me?
You're here? Yes, you're here. So you have 5 minutes, please, because we have small delay.
Okay, can you see the slides?
Yes, everything's working. Perfect.
Okay, so hello everyone. My name is Cornel Hovil and I am undergraduate student at the University of Warsaw. And I will have a very short talk about fitting Microlensing light curves. So let's start with simple Gsquared minimalization. Here you can see two models for Gaia 19 DKE, of which you have heard a moment ago. These are models from October 2020. The first one is without parallax and the second one is with parallax. As you can see, Gsquared is way smaller for parallax model. And thanks to that, we can say that in this event, parallax is huge. And it's very important information, and I will talk about it later. So these two models are looking good, but they are far from our final model, mostly because this is a very complicated light curve. And when we try to fit it, a cost function has many, many local minimas. So what we do instead is we take solution for a simple parallax fit and use it as initial values for Markov chain Monte Carlo method, MCMC in short. Thanks to this method, we can send thousands of walkers for search for local minimas around initial values. And to do that, we use MC module from Python. So here you can see possible solutions for Gaia 19 DKE. Each grade path is different solution. This could be simply degenerations of the same solution or completely different solutions. Most of them is obviously wrong, but as you can see, two of them are looking pretty good. And at this point, we couldn't really tell which one of them is the real one. But thanks to that, we know what to expect in a few following months. So this is a model from a year later, October 2021. And as you can see, only one solution remains from our two candidates. Since it's the only solution and it fits data pretty well, we think this is the right solution. So far, I show only models with Gaia only data, but as was mentioned, Gaia data have some gaps. So to improve our models, we use follow-up data, in this case from multi and LCO observatories. This is a huge amount of data, and it helps us to fill those gaps. Main problem is to choose the right follow-up, because as Katarzyna mentioned in her talk, some of the data are not good quality, and we have to check one by one which ones help to improve our models and which are not. So as you can see, in case of DKE, this is really the same model with minor changes in parameters. These minor changes are important, but mostly it is the same model. But in some cases, follow-up makes a huge difference. Here you can see two models for Gaia 19 BSY, which Łukasz mentioned in his Monday talk. As you can see here, Gaia data lacks data points around peak. And this is very bad because without this data, we can't find the right solution. So again, to fix this issue, we used follow-up, this time from LCO and MonSec observatories. As you can see, these are two completely different models. This one has only one peak and this two peaks. And Einstein time TE is 1.5 time greater in follow-up model, and this is a huge difference. And I will talk more about it in a moment. Why is it so important? So as you can see, follow-up is very important. So if you have a telescope or can contribute to follow-up, please do so. Because without good follow-up, we can't obtain true solutions for lenses like this. Last question, what are we doing it for? So as a result of MCMC modeling, we get parameters distribution. I won't get into details about each of these parameters, but as I mentioned, most important ones are TE and parallax PE. If we know these two parameters, we can, thanks to these two equations, approximate mass of the lens and distance to the lens. Typically, we want TE to be as high as possible and PE as low as possible, because this means that mass of the lens is high, and this could mean a black hole. Another very important parameter is blending parameter. This tells us how much light comes from the source, and if it's close to 1, it means that lens is dark. It's very important because it could mean that it's a black hole or other dark remnant, and this is very exciting. So thank you very much for your attention, and here's my contact info.
Okay, thank you, Kornel, very much. So we have the answer for the question from previous talk. And right now we will have lecture from Piotr Cionkowski, how to find the lensing black hole hiding in the light of its companion. Piotr, you have 10 minutes.
10?
Yes, we're shrinking it right now. So please.
Surprised?
Yeah, I'm surprised. Okay, thank you. So I will try to show a new method that I've been presenting in my master thesis of looking for black holes using microlensing. And black holes were pretty specific because they were accompanied by a light, like a third light usually. So we think of them as main sequence stars that were at the same distance as the black holes. So like the first part of my master thesis was figuring out how Gaia would detect those systems with their source stars. So here on the graphs, we have two cases, and there is a source that is moving usually for me in galactic nuclei. And there is a example of a blend, so like a star with a black hole as its companion. And the green curve is how the Gaia would detect those two objects based on the blending parameter, Fs. If there is a lot of light from the blend, then the detected source by the Gaia will be much closer to the blend. And if there is a little light from the source, it will be closer to the source of the lensing event. So we've defined, with Łukasz Wyszykowski, who was my supervisor, we've defined the blending parameter as flux coming from the source divided by the sum of the fluxes from the source and the blend. And it was used to define the relation between parallax detected by the Gaia, the blending parameter, the parallax of the source, and the parallax of the blend, which further allowed us to calculate the mass of the lens. And it's the same equation that Cornel has showed previously, but it's a bit expanded on a few parameters. So it's basically the same, just uses deeper relations. So the first part of the master thesis was to calculate the mass of the lens, and the second part was to calculate the mass of the light, let's say. So how did I do this? I've been using the table made by Eric Mamajek for stellar mass dwarfs in the main sequence. And according to this table, we can, based on the brightness of the star, we can assume its mass. Here on the far right. So comparing those to the value of the brightness of the blend and calculating it towards the mass, we can compare the said mass with the mass of the lens to see how much from the lens, how much mass from the lens is missing in the light. So to do all those things and compare them, I've been using Markov chain Monte Carlo method that Cornel has shown to figure out which lenses have solutions that would satisfy my requirements for them. One of the requirements was the event from the catalogs to be both in one of the Ogle catalogs that it could be cross-fitted with Gaia EDR3, and then that the object had the extinction calculated by OGL3 catalog. The third filter was using blending parameter, and I wanted bright blends, so the blending parameter had to be below 0.8. The parallax of the Gaia for me was, I wanted it to be higher than the parallax of the source, so that the detected object by the Gaia was closer to us than the source that I was expecting to be in the red cloud region, for which are the 6 and 7 filters to give me the lenses that had source star in the red cloud region. There's also a filter for Gaia parallax being larger than 3 of its errors to have results that were more precise, and Ruve parameter that shows the wellness of the Gaia fit, astrometric fit. So if the Ruve parameter is below 1.4, it shows that the parallax measurement is pretty good. So with all those things, I was left with 8 events. And to those events, I have added to Gaia 20 CFP event. And those I have modeled with MCMC method, which gave me 6 results, 6 solutions. Usually there are 2 solutions for each event, sometimes 4. They are symmetrical and give different parameters. And so for 9 lenses, I had 18 solutions, and 6 of those were good. I mean, there was the parameters were well defined for the microlensing curve, and the blending parameter was still below 0.8. And further, I have analyzed the light in the solutions to compare the mass of the lens at its distance and the mass of the lens with the mass of the blend. And here are shown the results, probability results for the mass being in certain regions. And here are the 3 best solutions, one for BLG 205 and 2 solutions for Gaia 20 CFP event. And those are the examples of how my results looked. And here are the final results of my master thesis, which show all 6 of the solutions with the mass of the lens, the distance of the lens from us, the mass of the blend, which is seen in the light. And there's a difference in mass between those previous 2 masses, which is calculated for each bin of probability separately. And the mass difference in sigmas shows us how probable is that there's more mass in each of the solutions, in each of the lenses than is shown in its light. And there are 3 good candidates, which is 2 events with 3 solutions, which is BLG 205 and Gaia 20 CFP. And we can further confirm those good candidates for microlensing black holes with bright companions through, for example, spectroscopy. And that's all of my results. Thank you for your attention.
Okay, thank you, Piotr. Any fast questions?
I have one more wait for the break.
If it's fast, you can tell it now, please.
Piotr, what is the parallax that you're using? Is it when you define the pi g? Is it the distance? Is it the parallax which is connected to the distance, or is it parallax connected to the the parallax, microlensing parallax?
It's the distance parallax.
Okay, thanks.
So the microlensing parallax, the PE, is calculated separately by the MCMC.
Okay, thanks.
Okay, thank you, Piotr, one more time. If you have any more questions, so please remember that we have chat and that we can always talk on the Slack. So remember about that and continue discussions there. And right now we would like to see the presentation and talk Zofia Kaczmarek, and she will talk about searching dark massive lenses through the dust. So please,
Okay.
Kasia.
Sorry, but I have a problem with sharing my screen at the moment, so just give me a minute, all right?
Okay. Kasia,
Just
możesz?
1 minute. Yes, it's
Okay.
all right. It's all right. I have to just reconnect.
Don't worry. I will cut your time.
I know. I know. My Zoom is reopening. I think sorry, I just had a system update and I'm still recovering.
Almost there.
Almost there, yes. Great. I have rejoined, and I am now. Yes, I am now sharing my screen. I think. Can you
Yes,
see?
we have it. Perfect. Slideshow, please.
Great. So, hello everyone. My name is Zofia Kaczmarek. I am a master's student at the Institute of Astronomy in Cambridge. And today I would like to tell you about something that is not directly related to Gaia alerts, but I think will be of interest to the microlensing community, to the transient community in general. And that is the search for dark massive lenses in the VVV data. And as a starting slide to feed your curiosity a little, I hope I am showing the picture of the Milky Way, but it's not the Milky Way as we know it, because the image is from the VVV. So we can see that it's a lot less opaque and we can actually see through the gamma test. I would like to acknowledge and thank everyone that
Is it hanging?
it is froze.
Do you want to use my gesture? The presentation is on Google.
Yes, it is.
Okay, so. Oh,
Zosia, is there any option that you can talk to us and during that time you will put the slides?
No slides, Doc.
Talk
Just like stuff.
without hands.
Describe the galaxy by shaking.
That would be pretty hard, I think. I don't really know what's happening because, like,
can you share the link on Slack? And I will open it on my.
Or maybe we can do another speaker.
yeah, let's just.
Okay, so Krzysztof Rybicki, are you there?
Yes.
Krzysiu, can you start your talk right now?
Sure.
Perfect. So Zosia, you will be after Chris, and right now, Chris, please try. Oh, fast boy. Thank you. You have your time right now, and it's 15 minutes with questions, please.
Okay. Thanks, Monica. So I will tell you about the event that you've never heard before. So Gaia 16 AYE. Just a quick reminder what it was. You probably all, or almost all of you were part of the research about this event. As it was already published, the analysis of the photometric measurements were published in Wyrzykowski and others 2020. So this is just the just an image of the points we all collected. We basically know now everything or almost everything about the lensing system, the lensing geometry in this event. So you might argue there is nothing new to show, but what we do have, the new developments is the astrometric data from Gaia, which helped us to learn even more about this event. So yeah, before going to the event itself, let me just show you quickly the astrometric microlensing. This is the normal, regular, boring photometric microlensing you already have seen in Kasia's slide, so you know what's happening here. But for the same geometry, for the same event, you can see when the source is moving, is passing the lens. We not only see the photometric change, but what is presented on the bottom panel is the astrometric shift of the source. So the bottom panel is the shift relative to the source position. So this is how it looks like for the very standard event, the single lens, and you know, as you know, this effect is very rare. It's hard to detect, because simply it's very small. The order of the shift is of the order of milliarc seconds or even sub-milliarc seconds. So it has only been detected twice so far by Sapel and others, and also by Zurlo and others a year later. But in both cases, it was a very special. Both events were very special, as the lens was very nearby, as you see, the most nearby lens possible in one of the cases, and lens and the source were actually resolved. So these were not the classical, as you would say, microlensing events. So we are so interested in this astrometric microlensing simply because it can provide something that cannot be learned from the photometry. So this parameter theta e can be measured when you model properly the astrometric effect, and then if you also have access to this pi e, which is parallax, you can derive the mass of the lens, and this is necessary to tell anything about the nature of the lens. So yes, so going a bit farther to the binaries, because Gaia 16 AYE has a binary lens. This is not the event. This is just an example of what is happening in the case of binary lens. You see this much weirder light curve due to more images appearing. But in general, the idea is the same. During the event, the total area of the images is higher than the area of the source. So we have increase in brightness. Now the same geometry, the same event from the perspective of astrometric microlensing. You see it can get even more crazy as the centroid trajectory kind of dances between these images because the light center simply changes. And on the bottom again, I'm showing the shift relative to the source itself. So it can get much weirder than in the case of the single event, but still this case is almost trivial compared to Gaia 16 AYE. So, and again, we do know this trajectory from the photometry itself. We do know what are the directions of the shifts of the centroid from the photometry. The problem is it's still in the units of theta e, in some internal units of microlensing. So by probing this ellipse or these weird shapes in case of binaries, we can measure theta e. But for that, we need astrometric measurements. So before diving deeper into microlensing, let me just quickly present what is Gaia actually measuring. So this would be just a simple trajectory we would see on the sky of the normal star, which is just superposition of its parallax motion and some proper motion. Now, imagine Gaia measuring visiting this field 4 times at the marked epochs. These are not Gaia measurements; these are just marked epochs of Gaia measurements. Now, Gaia would scan the sky in different directions for each of these epochs, and then we can plot for every of this epoch. Of course, this is not how the measurement itself is going. This kind of reverse engineering. We can plot these shifts if we know the model exactly, but we can plot this for every epoch. We can say what is the shift from the reference position for that epoch. So what is interesting, what is Gaia actually measuring is not this 2D position, but the projection of this shift, so these gray arrows, on the direction of the scan, which is marked with black arrows. So, for example, for these first 2 measurements, we would have very small signal in Gaia, because we see that these are almost perpendicular, and Gaia is measuring only in a long scan direction. Now, on the other hand, for the 3rd measurement, the registered shift should be large, because it's almost a long scan direction, but it's the opposite direction. So it would be negative here. And then again, for the last point, even if we have a very large shift compared to the reference position, it's almost perpendicular to the scanning direction. So it would be basically 0. So in Gaia, we would end up with these bizarre one-dimensional measurements, as is shown here on the bottom right. And we will have to model these with the knowledge we have about the spacecraft. So the basic formula for 2D shift would be simply some reference position, proper motion, and annual parallax. All the other quantities here are known, so it would be 5 parameter model. But in Gaia world, it has to be projected. This 2-dimensional shift has to be projected, knowing scanning angle for every measurement, on the direction, instantaneous direction of scan. So we would end up with this formula. We call this shift delta lambda, and it's still 5-parameter model that would fit to the simple astrometric solution for every star. So again, reference position in one direction, in second direction, 2 proper motions, and annual parallax. Now, going to the Gaia 16 AYE, this is how the blue points is how the initial data, astrometric data, look like for this event. We analyzed it within as a part of the process of validation of astrometric time series within DPAC. And first thing to do was, of course, to fit just this simple 5-parameter model. And you see immediately that something is definitely wrong here. We do see some residuals. The yellow dots are the model. So we did expect that, because we knew that microlensing was happening around that time. And as you see, between 7400 and 7800 reduced Julian date is exactly, here's 74, 78, it's exactly what is where the photometric, the most critical photometric changes were. So having that, we of course needed to extend our 5-parameter model to include microlensing. Now, first thing to do would be to model the light curve, so the photometry, but that was pretty simple because we already knew where to go, where to start from the study of Gsquared and others from 2020. So we already knew that it was there was every imaginable effect in this light curve, the binary lens, which was rotating, the finite source effect, the parallax, but we updated the model and arrived to the solution similar as Gsquared and others. So this is just to give you idea how complicated it was, because as you remember, I shown you before the let me stop it here before it gets messy. Before I shown the example of binary event, but the difference is that first the caustic there was static; it was not rotating, and second of all, the source trajectory, which is here in blue dashed line, was just a straight line. So here it's curved due to parallax effect. Now the red is the centroid of light, which is completely crazy, and you see this is how the geometry relative to the left panel is relative to the barycenter of the lens, how it would look like. Now it's still everything in the just from the photometry. So we do have this shift in theta e units. Now we have to reduce it to just a shift from the relative to the source, which would be the left panel here, right? Is after inclusion of blending, and this left panel, both of these panels is in normal.
Please, you're out of the time.
Okay. You didn't give me
so fast 1 minute and finish, please.
Okay, sure.
Thanks.
I'm getting there. So this is what would normally in standard event be an ellipse, and in this case it is this complicated shape, but it's pretty well sampled by Gaia. As you see, these are not measurements, just marked epochs by these black squares. So after some additional operations, we got to the model, the 1D model, which includes microlensing, which is here this last part. So this what we know from photometry is this delta lens, and then it just needs to be multiplied by theta e. And now fitting that to the Gaia data brings us to reproducing the data which are here in black. The bottom panel is residuals, and compared to the 5-parameter model. So you see that the deviation of 5-parameter model is large, but the microlensing model, which is in red, is pretty well behaved and going along the data. So that's it. I will just go to the conclusions quickly. I just wanted to say that we did measure theta e in using the time series of Gaia, and that it is possible to actually measure astrometric microlensing with Gaia data, although probably for some extreme cases. Now this is the image of the week. I'll just play it, and where you can see the photometry, astrometry, and the geometry on the sky shown together. And I'll take questions if there are some. Thanks.
Thank you, Chris. You are talking for 20 minutes, so you don't have time for questions. If anybody has any questions.
I really thought that there will be some warning, as usual.
I was waiting to you. But okay, any questions, please ask on Slack. Chris is still with us, so anytime you can ask him. And right now, Zosia is ready.
Yes.
I hope so. So please, Sofia.
So sorry once again for the technical delay. And yeah, is it working now?
You're not sharing the screen.
I don't know.
Yes, we have it.
Yes, great. Is it moving? Yes, it is. So I will just take off right when I started. So I would like to thank very much everyone who has contributed to this search in the US, the UK, and Poland. And I will start with a very quick introduction to the VVV survey, which is conducted by VISTA, a 4.1 meter telescope with an infrared camera. So VVV stands for Vista Variables Via. So it's a variability survey. It's an infrared survey that's conducted on this telescope. And all the data products are accessible. And it is the first map the map made by the survey is the first map that is large scale, not in just some narrow fields, multi-epoch infrared map of the galactic bulge and the disk. So in a way, it is complementary to the map provided by Gaia and other optical surveys. And there have been previous microlensing searches in the VVV, including the Navarro events, which were, the search was conducted in a way of very patient visual examination of sources from some narrow fields. But it was only in 2021, this year, where an automatic classifier has been published that made it possible to look for microlensing events throughout the entire VVV database. So you might ask, why are we doing this? And why are we looking for lensing events in the VVV when we have surveys that have superior cadence, accuracy, such as, for example, OGO? And well, the answer is very simple. We are not competing to find the same events. We are rather trying to fill the gaps in optical surveys where the Milky Way is obscured by dust. So if you plot our sample on top of, for example, the OGO field, so it will be similar with Gaia and all other optical surveys, you can see it fits very nicely into the very regions that optical surveys cannot probe. So those are also the most interesting regions because those are the densest, and we would expect a lot of interesting, previously unknown microlensing events there. So what we did with that sample containing 1,959 events was that we conducted models of the entire sample. And we were looking for just this, as you can see here. We were looking for this very subtle parallax deviation due to the Earth's motions. As Colonel said in his talk, we are looking for events just like this because very low but still identifiable parallax signal allows us to measure masses of lenses that are massive, so we can find our black holes here. How did we make it possible to model such a vast sample? Well, we adopted the nested sampling approach. I won't go into details here, but it's another method of modeling than MCMC that was used before. And if you want to have a visualization of that, I am providing here a link where you can look into it in detail. But basically, nested sampling is a top-down approach that just replaces the points that have the lowest likelihood with the points inside the likelihood contours. So we are shrinking and shrinking the contours until we find the most likely solutions. And the advantage of that is it's great for multimodal distributions. We get for free the relative likelihood of, for example, two degenerate solutions, as you can see here. It is very easy to automate because unlike the MCMC models shown before, there is no need for this human supervision. There is no need for cutting away individual solutions. And that's why we are able to fully automate the process. And with this use of automation and parallelization, because we run this on 30 separate cores, so 30 events were being modeled at the same time, we were able to run almost 4,000 microlensing models in what was about 3 days. So I think that was really amazing. And then with all of those models, we applied a simple cast of base factor over 100. So base factor is just a measure of how much one model or one hypothesis is preferred over the other. That is inferred from Bayesian statistics. What we got with this simple cut was this. So the map that I shown at the beginning was cut just to those red circles. So there were just 176 events, and we were able to easily inspect them visually, vote on them, score them, and now I would like to show you two candidates that made the cut with a perfect score. So this is just the beginning, but I would like to show you what we can expect from the sample in the future. So here is the first candidate that has like very huge gaps in the light curve, but still we were able to pinpoint the parallax and get the event parameters, which indicated really dark, as you can see, the high blending parameter lens. And just like for the previous lenses, we were able to get a mass distance plot. So Gaia cannot provide astrometry for those sources. But what I think is amazing that we have the positions from the DVB for each observation. There, obviously, you can't fit parallax to them. You can't fit the 5-parameter fit. But you can see the general trend and get the programmers from that. So what is amazing that the DVB with this astrometry actually uses Gaia as a reference frame, uses those very sparse sources in Gaia in the central regions to know where exactly we are. So we injected those proper motions into this code that tries to get the lens distance and the lens mass using galactic dynamics. And for this event, we found that it has a really low mass open to solar masses at a distance of about 3 kiloparsecs. And it's easy to stop the light of the main sequence starter. But we also have a further candidate that I think is my favorite, because even with the sparse cadence of VVV, we were able to constrain the peak really well. And for this one, we got the probability of the lens being a dark remnant of 99.9%. So this is an amazing result, I think, as this lens has not been previously found anywhere in any other series. And this shows the possibilities of searches in the infrared. So I would like to leave you with those very general take-home messages that firstly, infrared surveys can study fields that are inaccessible to optical observations, that infrared maps can be complementary to the maps we have from optical surveys. And I would like to inspire or encourage you to think about some possible synergies with infrared observations. And secondly, the use of machine learning classifiers, so the one that selected our initial sample of almost 2,000 events. And then nested sampling methods and from Bayesian statistics can greatly reduce the amount of human effort required for selecting lensing events and transient events in general, because this approach can be used to any kind of transients. And this is something we have talked about at this workshop very much, like how to reduce the human effort, the jobs that require a lot of patience. And of course, we can get rid of that in total, but instead of looking at tens of thousands of events, we just inspected over 100. So we would like to make the code and the tools we use for this public after we finish this analysis, so probably around the winter holidays, and we would like the community to use it and to make some great science. And if you have any questions, you can contact me by email. And I would like to say I also welcome questions on Zoom and here in Crete, but Monica probably won't let me. So I would like to thank you very much for your attention. Yeah, that's it.
Okay, thank you, Zosia. I will let Chris one small, fast question. Chris?
Very tiny. So.
Very tiny.
Hello, Chris.
Hi, Zosia. Nice talk. Are you using any publicly available Python-based nested sampling algorithm or some custom?
We are using Dynasty. It's a Python module for nested sampling.
Okay, thanks.
Okay, thank you, Zosia, one more time. It's really nice that VVV is opening for people. And thank you for your talk. Other questions, please, on Slack. And right now, the last talk before the break Ilknur Gezer, and she will talk about early recognition of microlensing events from archive photometry. Ilknur, are you with us?
Can you hear me?
Yes, we hear you, but we even see you. Okay. Can you share the screen with us?
Yeah. Can you?
Okay, so you have 12 minutes and 3 minutes for questions. And when I start waving to you, it means that your time is end. Okay, please start.
We can't hear you.
Now?
Yes, perfect.
Okay, I think I have a problem with my microphone. I hope now it's okay.
If you are not moving, it's okay. So try to not move your body.
Okay. So I gave this talk before, but we extend our study and we also developed a tool, but I don't know if I have time to mention about the tool. I will go quickly. Yes. So how we are detecting microlensing events. In Gaia Science Alerts, there are now 366 events which are labeled as a microlensing event or commented as a microlensing event candidate. So, but Gaia photometric measurements are not always enough to build the light curve. So we need ground-based follow-up. So that's why. So we need to select microlensing candidates carefully because we spend our network telescope on these events. And spectroscopic follow-ups also important for early recognition of microlensing events, but they are of course costly and limited to brightness of the event. And spectroscopic observations are important also to determine the atmospheric parameters and to define the distance of the source. So this is crucial for certain events. We also classify events from the light curve evolution, but this kind of classification we can do after when the event finished and completed. So far we had totally about 100 spectra for microlensing event candidates, and 20 of them also classified based on their light curves. So totally we have 120 objects. We know their nature, and this is our verification sample. So we know now we have classical BE stars, young stellar object, and asymptotic giant branch. These are the main sequence stars, and red giants are typical source stars in microlensing events. And the main contaminants are classical BE star, young stellar object, and AGB stars. So how we can detect microlensing event and exclude contaminants? So normally when we have microlensing event and when we took spectra, this is, for example, this is a typical microlensing event, and this is when the event was alerted. When we took spectra, we expect a typical stellar spectra. But in general, in BE stars and young stellar object, the magnification accompanied by mostly 1 or 2 Balmer emission in Balmer lines. This is, for example, BE star. This is the time of the alert. And when we took spectra, so we see that this is a BE star. And another example, AGB star, they have a very typical spectra with the molecular lines. And this is another example, young stellar object. This is the time of the alert. And here at the bottom, you can see again, there's emission in H alpha. So, but we cannot take spectra for all events. And these are some examples for light curve evolution. We know their microlensing event nature from their light curve evolution, but for this we need to wait until the end of the event. So totally we have 366 microlensing events published by Gaia Science Alert. Now they are labeled as ULens or commented as a microlensing event candidate. So we combined Gaia data with 2 mass and all-wise data. So we use archival photometry. So we explore the possibility to using archival multiband photometry for classification of the events. For all events, we have Gaia photometry. Only 250 have Gaia and 2 mass, and 184 of them have Gaia 2 mass and all-wise. But here, all-wise, only WISE 1 and WISE 2 photometry are usable. None of the 366 events have usable WISE 3 and WISE 4. So we had to use only WISE 1 and WISE 2. So what I said, our main contaminants are young-stellar object and classical BE stars, and sometimes AGB stars. So they are mostly dusty object, and this classification of young-stellar object and AGB stars have been the subject of many studies so far. I would like to show some diagnostic colors here. In the upper panel, you can see some diagnostic color diagrams without WISE 3 and WISE 4. And the lower panel, you can see if we would have WISE 3 and WISE 4. So you can see we could have more obvious separation. But unfortunately, we couldn't use WISE 3 and WISE 4. So what we did, so we built a training sample from the known object, classical BE star, young-stellar object, and evolved AGB stars. And the typical source stars in microlensing events, main stars and giants. So we split our sample in 3 categories because not all of them have these all Gaia 2 mass and WISE photometry. Some of them, like here, only Gaia photometry. Some of them have only Gaia and 2 mass, and some of them have Gaia 2 mass and WISE. So we used only colors because the observed magnitudes can affected by reddening. So we decided to use only colors. So we plotted the color. So maybe it's not so visible, but I can just say that we plotted the Pearson correlation matrix for 3 cases when we have 28 colors, when we have 15 colors, and when we have 3 colors. So the less colors available, so we can detect less class. So when we have 28 colors, we classified object into 5 classes like main sequence, red giants, YSO, BE, and AGB. When we have only 15 colors, we classified classical BE, YSO, AGB, and we combined microlensing events, microlensing and red giants. Sorry, the main and red giants. And when we have 3 colors, so we did binary classification. So this classification helps only to exclude AGB stars and young-stellar object. We cannot distinguish like classical BE stars from the main sequence stars. So we found that random forest classifiers give the highest accuracy during the testing phase. So these are the confusion matrix for 3 cases. So in totally 189 objects we classified with 8-band photometry, 66 objects we classified with 6-band photometry, and 114 objects we classified only with Gaia photometry. So we compare our photometric classification with the verification sample, which I mentioned in the beginning. So we know their nature from spectra or from their light curve evolution. So for 78 objects, we can compare 8-band photometry. So totally we have 35 microlensing events we know, but only 12 of them predicted correctly or with over 90% probability. Here, 17 young stellar objects, so we predict 4 of them with over 90% probability, including Gaia 20AEA. There was a talk about it yesterday, so we also predicted with over 90% probability, and BE star here and EGB star. So as I said, we couldn't use WISE3 and WISE4. It's unfortunate. So maybe we cannot predict too much event, correct? But we are sure about this 90% threshold. I will mention about that. So for 19 objects, we can compare 6-band photometry. So here we have 15 microlensing event, and 3 of them predicted correctly with over 90% probability. And from young star object, only 1 with the 6-band photometry. And 3-band photometry, here the important is this 8. So we classified 114 events with only Gaia photometry. And 8 of them classified as not ULens. That means they are either young stellar object or AGB stars. So I also plotted these 8 events here. This is BP minus G and G minus RP diagram. So it's see, this is only 3 colors, so it's more easy to make 2-dimensional visualization here. So you can see here these cyan colors. They are Gaia events. Maybe I don't know if it's visible. These red ones are AGB stars, blue points are young stellar object, and these square cyans are microlensing event candidates with only 3 Gaia photometry. These 8 of them classified as not ULens. As you can see here, they are very likely AGB star or young stellar objects, so they could be excluded. So that's it, actually. Thank you. But I want to say one more thing. Okay, this classification may look like, I mean, not many objects predicted correctly, but we know this with the 90% probability, all the classifications are consistent with the spectral or light curve classification. But the object classified with less than 90% probability, so in some cases classified into correct classes, in some cases classified into wrong classes. So we are sure that 90% threshold is very safe, but of course not so many events we can predict with over 90%. But when we classify, this is very likely correct class. Thank you.
Thank you. Almost in time. But it was okay. So any questions? Please raise your hand on Zoom. Or raise your hand in the lecture room. Okay, everybody are sleepy, as I see. So we have to start the coffee break.
Okay.
Thank you, Igor, one more time. I hope that after the coffee break, you will be more active and give more questions, please. So we're starting the coffee break. See in 25 minutes on Zoom and in the lecture room. So have a nice coffee, drink a lot and strong one. Please, see you soon.
Bye.
Mogę wrzucić
Hello, Łukasz, do you hear me?
Yes, I can hear you, Gsquared.
Yeah, I had a problem with my microphone.
Good, very good.
Update, but it's okay now.
Yeah, it's okay.
Okay.
Good, thank you.
I sent you an email about Gaia 20 BOF. It was in one of the presentations.
I will take a look. But let's not talk about it now because we are still streaming.
Okay.
Everything we say is streamed online. Josh, this looks very good. If you can hear me, this looks good.
I can hear you. Yes, thank you. Yeah, okay, it looks good. Yeah, I'm now on my laptop as well. Okay.
Great.
Thank you.
So now you can stop. Yeah.
Yes.
Arnaud, hi, we see you, but you can start sharing your screen already. We start in 1 minute.
Okay.
Okay, it's 5 o'clock, so we're starting right now. We have 5 talks today, and the first one is Arnaud Cassin. And Arnaud, are you ready?
Yes, I am ready. Thank you. Okay.
So you have 12 minutes and 3 minutes for questions.
Okay.
If I start, I will give you a sign that when your time will be ending. Okay?
Okay.
Great. So please.
So hello everyone. It's a pleasure to give this talk. I wish I were in Crete, but in any case, I think I would not have made it. So I'm happy to give this talk here. So I will talk about interferometric follow-up of Gaia microlensing event. And the analysis I will present today has been made by the team. A few people of the team are part of the conference today. So Bukaj, Christophe, Etienne, Rachel. Let me switch. Voilà, next one. So just before going, you already had some talk about microlensing. So let me give you a few facts about what we have observed. So during a microlensing event, as you know, you have many images of the source. So two images in the case of a single lens. And the important facts that will be useful for this talk are that the two images are aligned with the lens. So here you have the lens, you have the source which is unseen, and two images, the major image and the minor image, which when the source is very close to the lens, when it's a high magnification event, they become very, very similar. These two images at high magnification start to be strongly arc shape, and they are supported by the same angle here and there. So they are within this kind of within these lines, so they are the same angle here. The surface intensity is conserved, which means the magnification will be just, of course, the area related to the area of the image. And in terms of interferometry observation, we will consider that if the source is uniformly bright, for example, the image will be also uniformly bright, and they will have the same surface density intensity, which is an important fact when you compute the different quantities. When the source moves relative to the lens, the two images, of course, rotate, because this line will start to rotate, so the two images will rotate. The elongation of the arc is closer at maximum, and then it gets smaller and smaller. And when the source is very far from the lens, these are very similar to circular shapes. And the perfect alignment, of course, will give a single image, which will be the Einstein ring. So I will talk about the event we have been observing, Gaia 19 BLD, which was presented in January by Chris. This is a light curve. I will not detail the modeling of the light curve itself, but this is a view of the light curve of the full event. It was observed in 2019. Of course, it is very well sampled by Gaia data in red. It really samples the full light curve and even the peak. Also, very, very dense data from Hoggle, and many follow-up data from LCO and different sites around the world that made it possible to have this very dense sampling of the light curve, which is absolutely necessary if you want to retrieve important information about the light curve, the parameters. So this is a zoom in the peak region of the event, which shows the observation we have triggered for this event. So just to give you some information about how it was alerted. On April 18, it was recognized by Gaia Science Alert as a microlensing event, and then started a very dense follow-up observations. In July 8, it was alerted by Łukasz as a potential target for interferometry with Pioneer at the LTI. And so the modeling, the real-time modeling of the light curve was very important to try to predict when the peak should occur. And at this time, it was still very uncertain because there was about less than a week of uncertainty about the peak. But in any case, when you trigger a TO at VLTI, you have to be very, very flexible because you have to ask the people who are visitor to give you time, because as a target of opportunity, you are not priority. It's not priority to the visitor are the priority. So you have to negotiate a lot. And in 10 July, we triggered officially our target of opportunity, and we got three data, 3 sets of data in 12, 19, and 21st of July. And you see the trigger was there when we were sure that it would go beyond the magnitude limit of the instrument. So it's very interesting because actually we tested this limited magnitude of the instrument because we got another data set, another data there that was kind of given freely by the VLTI guy very nicely, but we got no data. We got no data because it was below this limit. So the limit is very well exactly what was expected actually. So we really tested the limit. So we got these 3 epochs that I will show you now. So these are the raw data, not really raw actually. These are reconstructed data with non-parametric reconstruction. So with some algorithm that make some assumptions, and this is what we got. And for many weeks, it was kind of mysterious, but before we really went to the study, of course. So because it's a very special event, it's not what we are used to, what people in interferometry are used to, let's say. So the signal, in fact, is here inside this blob, was called blob by a colleague. Voilà, it's a blob. And if you use this reconstructed image, you cannot do any science. You just see that there is some kind of elongation, but it's not really clear what's going on. So to do the modeling, we of course went to the observable of the interferometry, and these observable are the square visibility. So here on this plot, let's go on the plot on the upper plot. Here, for example, this corresponds to, I don't remember, maybe 19 of July, probably 19 of July. So we got in 19 July 2 sets of observation, which are this one and this one. Here you see the square visibility, which goes from 0 to 1. The data are the colored point. And as there was a grism, they were dispersed into 6 wavelengths. So to increase the span of how you probe, in fact, the squared visibility. And here, this is a 2-dimensional squared visibility, and these are where the spatial frequency where the data were taken. So this is how we sampled the square visibility with the data. And so the model which fitted very well at the end is really a model with arc-shaped images, as you can see here. So this is the final model, which shows that for this epoch, these are the arcs. So they are very, very thin arcs. So it was important. We had to develop some new algorithm to really deal with this very special geometry. And if you just for comparison, because the question has been asked many times, if you if you use, instead of using arcs, you use like just point-like images, which is what people do usually. But you realize that you don't fit at all the data, because here you see that this data, they will really probe the fact that the arcs are extended, so you have not only a pattern in this direction, but also a pattern in the other direction, because you have an extension around this direction. So the data are very extremely robust, and it really works very, very fine, very quickly. So these are the three epochs: epoch 1, epoch 2, epoch 3, 12, 19, and 21st of July. Two epochs, and only one epoch for the last one, because after it was too faint, and all data fit very well. And this gives you, without any knowledge of the light curve, this gives you the orientation of the arcs, how they are exactly like this, how they are oriented in the sky. So then what you can do is that you can now use a microlensing model, but still without any photometric data, just a microlensing model that tells you how the image rotates with time, assuming a straight line trajectory of the source relative to the lens. And you can link these all these three epochs, and it exactly gives this, so you exactly get the same results. So it's completely confirmed that the macrolensing event has rotating image, rotating exactly in the way we predicted by the theory. If of course, we know that in the way, but the first time we demonstrate this with interferometry, we could say. These are the closure phase. I will not insist too much, but if you have three epochs, you have basically two kinds of trajectory: east, west, or west, east, like this. And the closure phase can see the very, very small differences between the major and the minor image here. And it's very small, but still the effect we have on the closure phase tell us that the final model, which was the good direction, which is also derived by the photometry, is I don't remember which one of them. And it is exactly the same we get with the closure phase, although you see the error bar are large, because as the images are very symmetric, we expect the closure phase to be very, very, very close to zero. Voilà. So these are now in white the model where you see the image which rotating. I mean, the white model and the line joining the two images, and they are overplotted with an image reconstruction with an algorithm squeeze, which is a non-parametric, just taking without any assumption, and you see it's very well fitted. It corresponds very well. For example, here the arcs are quite large. You see that this blob is large, and here it's a bit less large, and here it gets thin, and it's really in correspondence with what we see at the end. So these are the first images rotating, monitored in real time, rotating gravitational images. Voilà, it's the first time we can see this in real time in a few days. So with this, we can do some very precise measurements. And this is my before last slide. We can, the Pioneer data, interferometric data, give you a very, very precise measurement of the angular Einstein ring radius. So you see, this is the data we got. So it's the precision is well below 1%. Yes. Timing,
okay. Please go
yes.
to the end.
Thank you. This is the end. This is the end. So, oops, no, this is the end. So we were able to measure to very high precision. Actually, the highest relative precision we could measure the mass, and it was interesting to see that since it was also observed by Spitzer spectroscopy and light curve, we could also test that this result was consistent between the two other methods. Voilà, I will stop here and just say that when instrument will get to lower, fainter event, we will have much more event to observe. Thank you for your attention.
Thank you very much. Okay, any questions? Maybe first one from Zoom. Siegfried, your microphone is working?
It's working.
Yes, okay. Okay, so please.
Okay, what is the fraction of higher alert events, microlensing events, I mean, that you could detect in this way using interferometric imaging? Is there a brightness threshold?
Is there
a brightness threshold?
Do you mean in how many events in Gaia we can observe like this?
Yes.
Okay,
yes.
so I would the main point is that you need the event to be bright. This is the main problem, the main difficulty. So you see that here. So Pioneer has a limit of 7.5 in H band, which makes quite bright because you need an event which is around 10. So there are a few events. I'm sure that Chris or Lukasz could answer better these questions in terms of percent, but it seems that we have a few targets per year.
Okay.
Well, I would say it's probably even less than this. It's like 1 a year if we are lucky. Yeah.
Okay.
If we are talking about these magnitudes, then of course there's less. But with another interferometric instrument, which is gravity, we can go fainter, and there is more hope. And also, gravity is now being improved to gravity plus, and we will be able to do this kind of stuff, as Arno is showing, for much fainter events, which are way more common. So this is kind of pioneering work using the Pioneer. And Mike, I actually have a comment on this. Actually, the plot you showed here, what Arno is doing here in this, and we've done in this work, this is actually time domain interferometry, which for us, the optical astronomers, is new. But I guess for the radio people here in the Zoom and the room, it's probably something what they do on everyday basis, right? And so I see a very nice kind of synergy we can find on this aspect. We are stepping into this new area of time domain interferometric optical measurements, especially in the context of microlensing events, while in radio.
অথচ পিএইচডিদের জন্য যদি এরকম করে হয় তাহলে সেক্ষেত্রে ইন্টারফেরোমেট্রিটা কাজে লাগে। আবার তোমার ইন্টারফেরোমেট্রি দিয়ে তুমি যে বেসিক সায়েন্সটা তাহলে আমাকে ইন্টারফেরোমেট্রি বোঝাতে হয়। হ্যাঁ, মানে তুমি এত কিছু তুমি 10 মিনিটের মধ্যে বলতে পারবে না। ইন্টারফেরোমেট্রি বলে এইটা বলবো এইটা বলবো। ইন্টারফেরোমেট্রির মধ্যে একটা স্লাইড রাখতে পারো, কিন্তু
I think I will mute you. Okay, sorry, Rupak, you were saying something, but I think it wasn't English. Sorry, I couldn't understand much, so I have muted you. Anyway, that was just my comment. So thanks for this.
Okay, any more questions? Anybody? Nobody. Okay, so Arno, thank you one more time. And now we have presentation of Algita. Algita, are you with us? Sharing. Yes, we see you, but we don't hear you still.
Hello, you hear me? Here?
Yes. Yes. Okay, so you have 12 minutes for your presentation.
Okay.
So please keep with the time.
Okay.
And
okay, I hope I will not be long. So today, hello, my name is Algita. I am 4th year PhD student at the Warsaw Observatory. And today I will be speaking about black hole microlensing, but with adaptive optics. So I will just go through. So why we need black holes? So black holes are one of the most, how to say, wondrous and amazing, how to say, sky objects in the sky that are, how to say, not well studied. So, and of course, we don't know exactly, scientists don't know exactly how they're, I mean, the different types of forming scenarios. So there could be many. So what we are doing, so we are using so-called gravitational microlensing phenomena, which a lot of people before talked about. And for instance, if we have, let's say, how does it work? So it works when we have so-called a star, and when we have our ground-based observatory or space-based. And when the lens, let's say lens object is passing through, it bends the light rays due to the gravity, due to Einstein's general relativity. And here you can see the light curve when there is, you know, here is the a lens star and where is an object, the light curve differs. So that's why we are moving to the ground-based observations, because ground-based observatories comparison to space-based, they are differ. Why? Because space-based are smaller, but they don't have atmospheric turbulence. While the ground-based observatories are way larger, but apparently they are facing the atmospheric turbulence, which is caused by so-called eddies or whirlpools, or they are in the different atmospheric layers, because our atmosphere is not uniform. We also have strong winds and different wind speeds, as well as how to say atmospheric pressure, temperature, and how to say light interaction with like for instance particles in the atmosphere. So that's why we have, instead of instead of a plane wave from space, we have a perturbed or disturbed wavefront, and we need to correct it. And how we will correct it? Of course, modern observatories, they are mostly equipped with adaptive optic systems, which is causing so-called tip and tilt mirror, which focuses our distorted wavefront to the deformable mirror. Here you can see you have so-called the wedges there. It's like a deformable mirror acts as a grating, because it should produce a diffraction pattern with the airy disk and diffraction limits. Then our distorted wavefront is corrected and it goes to the beam splitter, which is here. Then it goes to the wavefront sensor or Schack-Hartmann wavefront sensor, and our corrected wavefront goes to the CCD camera. So that's how adaptive optics works. And then moving forward to the VLT or very large telescope. So very large telescopes has 4 unit telescopes and 4 auxiliary movable telescopes. The unit telescopes are 8.2 meter in diameter. All of them has the same diameter. So NACO is the adaptive optics system, was apparently, because it's already decommissioned. So it used to work with unit telescope 4, but it was moved from 2013 to unit telescope 1. It provides, of course, adaptive optics imaging, coronagraphy at the L band, and it was decommissioned in 2019, so very recently, because it has a new predecessor, which is called the Sphere. So what we did, we took 2 images of NACO in 2 bands, H band here and K band. Here you can see our target star is in the red circle. So we took, we extracted the point spread functions from that. So we use the analytical equation, which is was written in this paper, because it was used for completely like for the NACO data. So here you can see this equation had many parameters, which some of them are describing the sky background, and there are amplitudes, widths, center of profile, and of course the parameter that describes rotation. So we extracted the point spread function from the image, and then we fit it up. So here we can see this is a fitting. then what we did 3D, how to say, view. The purple is the image, and blue is the fitted function. Then we extracted all the point spread functions, and here you can see we have like the, how to say, they're quite similar, but apparently we didn't see the, how to say, another let's say peak that will tell us that we have so-called black hole microlensing. So we then we, how to say, we show the plots that we show the detectability of let's say of the black hole, and I'm currently finishing that. We hope that this event supposed to be caused by a black hole or a very faint sequence star, and apparently we need more, how to say, more precise investigations on that. And in the conclusion, I would like to say that modern adaptive optic systems, which are equipped with even not single conjugated adaptive optics as NACO had, but multi-conjugated adaptive optics, can lead us to have more results and more investigations. So I think I'm on time. So thank you for your attention.
Thank you, Olgita. Okay, so do you have any questions? You already have your coffee, so come on.
No, I didn't have coffee. There is more coffee probably outside.
Yes.
So ask your question and go for coffee.
Exactly. You can't go for the coffee if you don't ask the question. Nada, please.
So the light curve that you showed, I mean, I already started. Can you have it here?
Excuse me, I cannot hear you, Nada.
Have to come closer.
Right. I'm sorry. Yeah. So the image that you showed.
So
yeah,
we
so
took this one is a target star, yeah, and we took the PCFs of this.
Yeah. So this one was a microlensing event. I mean, how did you? And what was the light curve of the event? Do you have it? I mean, is it, you know, so were you able also to get a model out of it from the light curve?
No, we just extracted the point spread functions with the code, and we fitted by this one because we had analytical equation, and that's why we just needed to fit it by this analytical equation.
Okay. Okay.
But may I comment something?
Of course.
But these are known microlensing events.
Okay.
Yes,
so we have already
so
microlensing model and the light curve.
Okay, this part is not. That's what I was.
Yeah. Of course, it's known microlensing. Was all gold something.
Okay, Kasia, question, please.
For these events, from what time period these events are they from like 10 years ago, or are they current events?
No, 10 years ago it was a wait where I can find which one it was. Yeah, which one?
It was about 2005.
Yeah, 2006,
something.
5. Yeah, 2006. So it's more than 10 years. So it's not correct.
Okay, so we're hoping for the separated source and lens, right?
Yes.
Yes,
okay,
exactly.
Okay, any more questions? Anybody? Nobody? Okay, so thank you, Olgita, very much. And right now, Etienne, are you there?
Hello.
Okay, Etienne will tell us about the Omega Key project.
Yes.
We see you. Can you share the screen?
Yeah. Okay.
We hope that you're fine and you're not tired and sleepy because of the time which you have in your time zone.
I am sleepy.
Yeah. Okay.
But thanks for asking.
To not fall asleep. Okay, please start.
Do you see the screen?
Yes, we see everything. You have 12 minutes and 3 minutes for questions. Please start.
Okay, thank you. So yeah, today I would like to present some of the results we get from the first year of the Omega project. So the Omega project is a project that intends the follow-up of microlensing events in the sky, and it's a collaboration between LCO and many institutions and people all around the world. So our main motivation is to try to find cold planets in the entire Milky Way. So here I display on the left the distribution of known planets in the mass versus the distance to the snow line, normalized by the snow line of this planet. And what we can see is all the methods of detection are very complementary because transit and radial velocity are very sensitive methods to detect planets close to their host star, so inside the snowline region. But their sensitivity drop after the snowline. But fortunately, this is where microlensing and direct imaging are actually the most sensitive. So combining all of this method of detection is very efficient to characterize the planet demographics in the parameter space. And also on right, I display the population of known planets in the Milky Way schematic view. And what we can see is only microlensing is capable to detect planets at several kiloparsecs from the Earth. So far, we have detected mostly planets towards the galactic bulge because this is where the survey, the microlensing survey, focus their efforts, and especially Ogle and Moa. So another object of interest is stellar remnant, and especially stellar mass black hole. And because the duration of microlensing event is proportional to the square root of the length of the mass of the lens, then if you observe a black hole lens, then the event is going to have a very long duration. And from this, you can extract some property on the mass of this potential black hole, and we can see that on the left, microlensing has the capability to complement other methods of detection of black holes, such as LIGO-Virgo black holes and black holes around X-ray. We live in a day where there is a new potential for microlensing, and this comes from a new generation of all-sky survey. So here I display a few, especially Gaia, ZTF, Tomo and Gozen, and Assassin. And in a very close future, we're gonna have LSST. So all of these surveys are great because they survey all the sky very often. But it's unfortunately they don't have a very high cadence. Here I display the first year cadence from ZTF. We can see that for the most dense field, we can expect a few points per week, which is not enough to have a good constraint on the microlensing models. So here I display on top the potential that LSST for microlensing. We can see in this galactic view the number of events per degree square per year, and it is clear that LSST is going to detect thousands of events every year, but again, it's going to be very with insufficient cadence of a few points per week. So the Omega Key project intends to make the follow-up of all events detected in the entire sky, and to do so, he used two main follow-up modes. The first one is photometry. We trigger two bands, SDSS I and G, for the event characterization. And we have 3 modes of observation, which are, one is regular, which is a standard follow-up of event. We can trigger priority cadence if events start to reach high magnification potential. And we have an anomalous mode, which is a very intensive mode when the event turns out to be anomalous. We also plan to do spectroscopy with too low resolution fluid spectra, and if possible, we want to have high resolution spectra using NRES spectrograph at LCO. So spectroscopy is very important for us to first identify false candidates. So here I display this event from ZTF, which can look like microlensing, but the hash alpha in emission that we collect with the fluids make us suspicious about the exact nature of this event. The second one is to estimate the spectral types. It's very important for events which are not in the bulge, where the characterize the source is more difficult. So here I display the example spectra we get for Gaia 19 BLDs that are not present previously. We get VLT and NRES spectra that converge to similar stellar types. And by fitting the line and fitting template matching, you can estimate as well the extension and the angular radius toward of the source star. So the Omega Q project rely on the microlensing observing platform. It's a TOM toolkit database deployed on Amazon Web Server cloud computing. It's very it's similar to black hole Photom, where I'm sure you are more familiar with. And the idea of MOP is to do everything automatically, and that starts by brokering, by harvesting all microlensing candidates that various survey found, such as Ogle, Assassin, ZTF, etc. Then the idea is to fit all of this event in real time and rank them by obtaining priority. And to do so, we can use the capability of AWS to make massively parallel fits. And then, as needed, and following our strategy, observing strategy, we can submit extra observation to the Las Cumbres Observatory telescope network. And we have implemented a new real-time DIA photometry pipeline in Python that delivers a real-time photometry. And then the loop is complete. We can reassess the event and resubmit observation as needed. And the ultimate goal, of course, is to obtain new microlensing science. This year, we have 2 students at LCO that help us to develop new features on MOP. Nicole developed a new broker for Assassin event, while Claire Lewis, she developed the observing tools that we needed to support the installation of Muscat 3 on our 2-meter telescope in Hawaii. So that is now implemented. So to give some results for the first year of Omega, we have at the time 1,100 event monitored, but let's say 3/4 of them are toward the galactic bulge that is expected. We have about 300 events in the galactic disk, and for those with monitor about 400 of them in photometry, and we collect about 78 spectra. And we have a special category for events that show a particular scientific interest. We call them event of interest, of course. And for so far, we collected data on 15 planet events. Of course, we have also a dozen of binary lens and several remnant candidates. So here I display a very recent event. It's called Gaia 21 EFS. We had a very dense follow-up for this event because it was reaching high magnification. Unfortunately, it didn't show any planetary anomaly yet. Another event that I already presented last year, which is Gaia 20 BOF, at the time our real-time modeling show It was maybe a planetary candidate. It seems the most recent modeling leads to a very close low mass binary star lens. Here is another example of events that we follow, which is a paper that Katarzyna is submitting. Gaia 18 CBF. We can see the two models of this event in blue and red lead to a very massive length of more than 2 solar mass, but with we know that the lens is not luminous, so this event is very likely a stellar remnant lens. Final example is Gaia 20 AUW. Here I present a model made by Chris, and we can see that this event show very strong caustic crossing that we very well follow up with omega. And in fact, there is two things interesting with this event. It seems we need orbital motion to model it because of this long time scale of 70 days. And in fact, it seems even the full Keplerian orbital motion is probably constrained, and so we should be able to make some assumption about potential RV follow-up. And also here I display a zoom around the caustic crossing. We see that the space parallax is very well covered, so we're going to have a very strong constraint on the mass of this lens. And from this, I will thank you all and take any question.
Łukasz, please.
Very nice stuff at the end. But the one you showed, the last one you showed, the binary, AUW. Is it AUW or CCU? Because you have misleading comments. Which one is this actually?
Oh, yeah. As I told you, I'm too tired. I think it's AUW. Sorry, yeah.
The first one is AUW, and the second is CCU.
I see. So space parallax is in CCU.
No. It's the same. It's the same event. That's for sure. It's a Gaia 21 AU. So this zoom here is the zoom of this event.
All right.
Sorry.
Thank you.
Actually, they are similar targets.
CCU is much brighter.
Yes, that's the difference.
Yeah, that's right. They look similar.
Okay, Josh, your question, please.
I just have a comment. Indeed, I am observing Gaia 21 CCU, and I will show it tomorrow. So it has this kind of shape in my photometry.
Okay, great. We will see it. Okay, any more questions? Anybody? No?
So maybe me.
Okay, Paweł, please.
Hi, Etienne. Paweł Zieliński speaking. Yeah, very nice talk. I just wanted to know more about the method of target selection, of your target selection. You said that you have selected more than 1,000 events and you monitored them, but how did you get this 1,000 from the large amount of transient?
Okay, so what we do is we try to catch things. So for example, for the classical bird survey as MOA and Ogle, we just take everything that deliver every year. Unfortunately, Ogle has stopped since 2 years now, so of course we don't have their events, but we really hope they're going to start again next year. So we take all MOA events. We also plan to probably harvest KMT-net at some point. It has to be developed. So that's the first thing. And for other events, we have created brokers for Gaia, ZTF, Assassin, etc. And for example, for Gaia, the way it works is going to the alert index and just collect all events where microlensing is written as a comment. And of course, that means sometimes we have false positive, and sometimes we also miss some events that are in black hole term, for example. And that's why at some point we're going to need to develop tools to cross-match target between, for example, different term toolkits, I believe. And for ZTF, we used brokers that Przemek Mroz developed. He gave us a list of potential candidates. And for Assassin, we use something very similar to Gaia. We go to the Assassin alert index, and we catch every row where microlensing is present.
Okay, thanks.
Bravo for your question. And Simon, you have some question?
If we have time, thank you very much. It seems to me that the more and more light curves of Gaia microlensing events I see more and more evidence of binarity in the lens. This one, CCU, also shows evidence of this, as well as the one Łukasz published. Can you comment on what the binary fraction of the lenses might be of this population?
So, I would say from statistics of microlensing event to galactic bulge, I would say about 10% of events are expected to show binarity. So of course we know that it should be more than that because the binary fraction is higher than 10%, but it's just sometimes you miss the caustics, so you just see single lens where they are actually binary. But I would say that we should see about 10% of events should show binarity. If we have similar efficiency and population as we have toward the galactic bulge.
And good enough, prompt enough optical follow-up to be able to see the shape of the light curve.
Yes, so I think, for example, in this case of I display here, if we didn't have coverage from ground, probably just the points from Gaia would not have been sufficient to assess if it was binary or not.
Exactly. Thank you.
Okay, I don't see any more questions. So thank you, Etienne, one more time. It was really nice.
Thank you.
And right now I would like to, Ashish, are you there?
Yes, can you hear me?
Yes, we hear you, we see you. And now we see your presentation. So fast highlights, please. You have 25 minutes for your presentation and then 5 minutes for questions. So please.
Okay, thank you. Yeah. Good evening, everybody, and thank you for inviting me, and also thank you to Łukasz for moving my talk to day 3 rather than day 1. I just traveled 3 days ago from the US to India, so late time plus jet lag, we'll see how it goes. But I'm going to talk about a few ZTF highlights. And it was good to see some ZTF discussion in the last talk as well, because I'm going to leave microlensing out. You already heard a little bit about ZTF related things from microlensing. So for those of you who are not fully aware of what ZTF is, here is a brief summary. So we use a 1.2 meter automated telescope at Palomar. The field of view is a whooping 47 square degrees. We go to about 20.5 magnitudes. The exposures are 30 seconds, and we use GRI filters. For the public survey, it's mostly G and R, though I has been used a little bit there as well. We get about 1.4 terabyte of data nightly and 20,000 square degrees every 2 nights in G and R. This is the team. You see the leads of various things. I lead the machine learning part of ZTF, but also there are a large number of other people who are the real stars doing lots and lots of different very interesting things, and I'll try to summarize a few of those. But before that, let me quickly summarize the DR8, which was released just a few days back. So we are now on this 2-month cycle. So every 2 months, there is going to be a new data release. And you can see some impressive numbers here on the bottom left, for instance. When you combine the GR and I filters, the number of source points that you can see is about 500 billion. And so you can have light curves in individual filters, which are quite impressive. And especially when you combine these with other sets like Gaia, which is fantastic astrometry space-based somewhat different colors or older data, then we get a very good archival set. So one thing that we have been looking at is we have been doing very good real-time work, but also looking more and more at archive and the power of archives, how they can provide fantastic science. Here's a brief coverage in G, R, and I, and we provide an API as well. So here's an example query that you can use with API. And if you go to ctf.caltech.edu, you can get all the details there. So all the DR8 is at your fingertips, for instance. The main science drivers of ZTF include essentially a fast, wide area time domain survey and anything that you can find there at the cadences that we have. So there are many, many rare flux transients, counterparts to gravitational wave sources, lots and lots of supernovae, and I'll have a few slides related to supernovae later. But when it comes to archives, for instance, the variable star stuff and eclipsing binaries, those have been really stellar stars of ZTF, and lots of things with solar system objects also. I'll have a few highlights there as well. So the exemplars that I'm going to present are going to be not going to be exhaustive, but more sample. And also they're likely to be biased more towards the areas that I work in or I'm better versed in. But I'll provide examples of the things that I mentioned there. In technology and infrastructure, that is one area where I'm very interested. I work in classification, so I'll provide you the details of our scope architecture, which we use for stellar variability. But when it comes to transients, we have all of these things in extragalactic. We have got supernovae where SCDM is used to first classify 1A and publish them, but also we have been doing a lot of classification of other supernovae. We've been using time series combined with these low resolution spectra, lots and lots of TVs. And then in solar systems, comets and streaky asteroids, the near Earth asteroids also have been doing a lot of machine learning with those. So the main currency of ZTF is an alert packet. And the alert packet consists of 363 by 63 32-bit images, the new recent image, which is a 30-second image, a reference image, which is a coad done properly of older images, and a subtraction image. And the subtraction can be negative when we find that a source has become fainter. So those are also there. And along with it comes a light curve, which is a rolling 30-day window. So you don't get a light curve from the start of ZTF, but the last 30 days. But what we have started recently is also a forced photometry service. So you can go and query ZTF and ask for photometry at a specific point from images that would be in the archives. Then what we also have is that there are many, many metadata parameters that go with these alerts. So it's essentially a very rich, high dimensional space on which one can do lots and lots of things. And these are served from, they go from Paloma to Caltech IPAC and to University of Washington, and Mars also from LC also serves it. And then many brokers that will be working for the Vera Rubin Observatory are currently consuming these and doing very interesting things with that. So when it comes to technology infrastructure, what are some of the things that we have been doing? We started with BRI long back because we needed a real bogus classifier with 100,000 alerts. We wanted to be sure that we provide some kind of confidence with that. And so the BRI classifier was born, and it has been used in many other areas also. So those get consumed by these alerts and brokers. And we now have a new set of filters called the ASI filters to better explore the parameter spaces. So these are 5 binary classifiers which look to see whether a transient has a host or whether it is an orphan, how likely it is to be a bogus despite the fact that BRI thinks it is a real object based on many other additional parameters. And then what we'd like to see is if it's nuclear, is it likely to be an AGN or a supernova or a tidal disruption event? So some nuances related to that go into that ASI filter as well. And then we'll talk of scope that I mentioned. We have been doing a lot with trying to find anomalies with sources. First of all, what one has to do is that sources that escape our real bogus and have some quirky points because of something that we could not catch because there weren't enough examples, those we want to catch. But then there are truly anomalous objects also. So we have recently started doing more on that. And then the SCDM and supernova classification. So we'll see how much we can spend on each of these. And on the right-hand side, you see the FRITZ infrastructure, which is our advanced Marshall, which we use to do multiple things, scanning alerts, but also for the scope related things, doing active learning when we get lots of objects and we have some ambiguous classification using human neural networks in addition to the machine learning that we do with the other neural networks. So let's start quickly with the BRI real bogus separator. What we had was that 3 images, the science, reference, and difference images, and now what you can call a vanilla neural network was used there to do the classification, and it's been quite successful, the numbers that come out of it. So these are the FNR and FPR, the false negative rates and the false positive rate that you can see with that. And you can see that they're really low where they cross over, and that is why the filter has been very, very successful. So coming to the source classification project now, what here we have been doing is that we took the light curves that we had from DR2, now we are on DR8, but this is where it started. And then we took 20 of the ZTF fields. You see the field distribution at the bottom right, and there are several hundred ZTF fields. And we chose 20 to be representative of the entire set. So some of them are low galactic latitude, some of them are high galactic latitude, some of them are low declination, some of them are high declination, and so on. So a good combination of those. And those 20 fields had about 34 million objects. From those, we obtained features, a large number of features. These come as 3 different kinds of periods were fit. And then we use the DMDT to look for how the structure function of each of these light curves looks, because the gaps are very irregular. And what DMDT allows you to do is that bring them on par with each other. And then we also use external data like Gaia and Pan-STARRS to combine with that. And so the features that we had were about 50. The 3 different methods that we used for period finding were conditional entropy, Lomskargel, and analysis of variance. And then the cross-matching, in addition to the 2 that I mentioned, there are up to 10 catalogs that we use for doing the cross-matches. And then when you look at the period finding and some of the early features, we looked at their distributions, and the simplest filter that one can build after the real bogus is a non-variable versus variable, because you want to get rid of the non-variables, which can be 80 to 90% at the error levels that we see. And once you have the variables, it is then that you want to try to separate them into various subclasses. So just trying to understand which of the variables are good for doing that, given that we start with about 50 different variables, 50 different parameters. And those parameters have been combined from a large number of earlier studies that have been done through Caltech surveys as well as external surveys. For instance, in DPOS as well as Palomar Quest, and then with CRTS, we have been using a large number of variables. So we combine parameters, we combine those and many of the external ones. So in this first set that we had about 200,000 individual labeled light curves, and many of them were labeled within ZTF, but we also imported labels from CRTS, UGL, etc. And clearly what that means is that we had unbalanced classes. Not only were these unbalanced, but they were also biased. They were biased in the sense that some of the labels came from external sources, and when they come from external sources, the biases that those surveys had got imported. For instance, they would have a different magnitude limit, or they would have a different filters, and how objects looked in those filters was what got in. And that is what we had to do, is that a lot of active learning, understanding how those biases could be removed. And we used something called label smoothing there. So the values were quantized to 0, 0.25, 0.5, 0.751. So 5 discrete values from 0 to 1 essentially. We asked ourselves that when an object looks like, say, an RR Lyrae, how confident are we? 1 would be confident, 0 would be not at all. But we didn't want to leave out objects where we thought it was an RR Lyrae, but maybe there were other possibilities too. That is where these intermediate values came in. And when we came back for inspecting those, that is where we looked for all these things. Are the objects where we are most confident about, one way or the other, close to 0 or 1, but also close to decision boundary. And those are the most difficult sources, but those are the ones which are going to help us disambiguate many, many sources into not only different classes, but also different subclasses. Because as we go deeper into the decision boundaries and hierarchy trees, we're going to learn more and more about classes that seemed rare before, but with the newer surveys, especially across the archives and different time intervals, we can start to unravel. So we had this cycle a large number of times, select and inspect, and then predict and label, add to training set, retrain and repeat. And we did that during this scope 1 for the 20 field survey. And then we marched down the nomenclature tree. That is where what we started doing was several binary classifiers rather than a single multi-class classifier. You see the two workflows there. And we used two different types of classifiers as well. We used the neural networks and XGBoost, and we did hyperparameter tuning for those. So we do have in mind combining these, because once you start combining them, that is going to give you far more power than a single classifier would do. Because not only do the data have their biases, but the classifiers have their biases also. And to disambiguate those, again, if we could do a meta classification, then it would be far better. But it's simpler, easy to say that than to do, because meta classification involves a good amount of work. Recently, we published different work unrelated to ZTF on the O3B catalog. So this was work with some folks in Canada that we did, to young students led that, and you'll be seeing, I think the paper was on archive yesterday. So where we classified the O3B objects before the O3B was released officially by LVC. And there, for instance, we had 3 different binary classifiers, and then the performance of the 3 classifiers is different from each other. And that is where combining them becomes quite interesting, because if we were to go with one classifier, we are confident about one set of sources, but another classifier is better at some other sources which overlap a little bit with the first one. And all that needs to be taken into consideration. So this is how our t-SNE distributions look. The diagram on the top right, both brain-like diagrams, is just variables and non-variables. But when you remove the non-variables, you see that underneath that are a few variables. So you can see distribution of those as well. And then you can see that there are overlaps between some of the classes, and that the t-SNE is not the best of 2D separators, but that's an easy to put together, and we are exploring additional ones. But to tease apart those classifications, that's a good starting point. And then this is the hierarchy that we currently have. We also have 2 different kinds of classifications, so phenomenological and ontological ones. And within the phenomenological ones, what we do is that we simply try to see how the light curves look meaning in terms of the features that we have without using external data. And then along with that, we use the external data to do the ontological classifications, where we go to individual types, individual classes. So that is where you see the beta Lyrays and RS Canvans and W-UMAs, and also AG inversos, etc. So essentially, because each of these classifiers is done separately, their confidences, their probabilities are not additive to one. And that restriction allows us to put multiple labels on the same object. So this is somewhat related to what Simon was asking a couple of days earlier, as to when you have a large number of classifiers, what is it that you can do with them? And it's something that's not fully solved, but we are getting better at it with all these binary classifications, holding a large number of confidences along until you need to resolve them. So when you need to go and take a spectrum, then you do your best thing at that point and decide whether you want a spectrum of an object or not. But otherwise, it's better to keep it ambiguous until more and more points come, because there are other techniques that are being developed where, given a light curve, which seems ambiguous, it may fall into different classes. What single observation taken when is going to disambiguate best? So those are the things that can be done if you leave the probabilities going along. So you can see on the top left, our RR Lyra classifier, or for the input set of RR Lyra is how the different classifiers did. So the first vertical column is variable versus non-variable. And the yellow there close to 1 indicates that that classifier did say that RR Lyrays are variables. The next one says also that they are periodic. And then you see the yellows at the bottom close to 0. Several of the next ones, which include the flaring ones, eclipsing ones, irregular ones, telling you that RR Lyrays do not belong to those classes. And then when it comes to pulsating, again, you see close to 1, And then the next close to one is RLI, ontological classifier itself. So this is fairly good. And then because of the unbalanced nature of the data that we had, we found some interesting comparisons between the XGBoost and DNN. In some cases, XGBoost was better than DNN. And in some other cases, the neural network was better than XGBoost. And that is where the parameter tuning comes in a much stronger fashion. So that's something that we are exploring much more as we go to classifying an entire data release. And so that's where we will be adding more and more classes and subclasses. But as we do that, the anomalies that I mentioned, we are starting to look for those, putting in more active learning. We have not gotten to meta-classification yet, but meta-classification and interpretability, those are two things we are starting to look at together, because we don't want these to remain as black boxes. Given the 50-dimensional parameter space, we need to understand better why something was classified as a specific type and whether that's repeatable and so on. Another interesting thing that we have done recently is adding a fast readout mode to ZTF. So here, what we do is that the telescope, the charge that we have that is being accumulated due to the photons is read out almost continuously. And so we get a resolution of about a few milliseconds. And so each star leaves a streak along the horizontal. And what that means though is that there could be two stars that are along the same pixel and you'll see them overlap, but then you'll be able to disambiguate them based on the starting point, because at the starting point, you see dots and you can use that to see how that goes. And then objects that are transients obviously will look different, and objects that are moving will leave an angle in general along with that. So what you see there is one such thing. One could look for fast radio bursts with this, or you can look for rapidly spinning space debris. So lots of interesting things there. And of course, because it's not a very large telescope and you are integrating for a really short time, you can go only up to about 12.6 magnitudes at an SNR of 10. But even at that magnitude, one can find interesting objects with this. So that's something that's ongoing. We have been spending about not too many hours on this as we improve our data analysis for this, but that's something that we may be spending more time on. Then let's move a little bit to supernovae, because I know that many of you are interested in supernovae. So there are two main surveys that are done. One is flux limited, going to 18.5 magnitudes, because then we can take spectra of all these objects. Another one is the volume limited, going up to 200 megaparsec. And you can see that the two numbers at the bottom left, 5,600 for up to 19th magnitude and more than 3,700 for 18.5 magnitude. So a large number of supernovae clearly. We've been finding one infant supernova every week with the spectrum available within 24 hours. What this means is that we are really now in the statistical domain. There are interesting individual supernovae, like some of the superluminous supernovae, for instance, and there will be papers written on that, but we are really in an area where we can do interesting statistics on that. And so the few papers that I mentioned here are doing something like that, trying to look for, say, two supernovae in the same galaxy, or trying to look for additional interesting things in terms of characteristics. So not just for supernovae, but for other areas also, we can do quite interesting statistical things. For AGN, how many times do you think, and do you see that the central brightening that you see is somewhat offset from the center, which may mean there is some black hole activity, something being pushed out and so on. So there are various other types of transients too. And again, I would like to emphasize that this is not an exhaustive thing. There is a list of papers that you can go and look at it. For instance, there's new candidate black hole with low mass X-ray binary, or helium-rich superluminous supernovae. There are many papers about afterglows, TDs, AGNs, and of course, a lot of work on binaries and strong magnetic fields that you'd be looking at. I'm going to just skip that, but you'll find more details of it in many places. I will quickly mention the supernova classifiers though, because here what we have been doing is that since we find so many supernovae every night, we have been using the low resolution spectra along with any archival data. We have to quickly classify them. And now our workflow is such that within a matter of minutes, we can do the classification and it is sent to the TNS. And Christopher has been leading this work. Besides the classification, besides identifying whether a transient that we see is a type 1a or not, what we have also managed to do is that get a regressed redshift out of it. So you get of the galaxy, of the host, clearly. And once you get that, then you can start getting an understanding of the distribution better. And if you want a better spectrum of it, if it's farther out or closer to what you find and so on. In addition to the type 1As, a difficult question is about what is left after that. So Yashvi has been doing some classifications on that. So the SN1A score that we use is 0.9. After that is out, a bunch of other things are left, all kinds of other supernovae, but some of the other transients that are not supernovae are left in that also. And initially those classifications were all done manually, but that is where now what we have started doing is a spectral classifier that does additional things with that. And these are how some of our numbers look. So the first step that we do is separate the AGN and CVs that may have snuck into those transients, which initially look like supernovae for whatever reason, but are not. And then we can do that now to 94% accuracy. And having removed those, then the best that we can do is whether they're hydrogen rich or hydrogen poor based on the couple of points we have and the very low resolution spectrum. And there we can do it at 87% accuracy. And the main bottleneck there really is the smaller numbers that we have for individual different kinds of supernovae. Though we have got 3,700 at 18.5, a majority of them are either supernovae type 1A or a scattering of the other ones. But this is again improving rapidly. And then with the solar system, quickly in my last 2 minutes that I have mentioning things about solar system, we have been finding many objects within the Earth's field. So we found the 2019 AQ3 and then another one which was 1.2 kilometer in size and also inside the Earth's orbit. But then we found an object that was inside of Venus's orbit. And existing models suggested there would be one such object, and clearly we are not exhaustively observing everything. So our models, everybody's models need corrections. And there have been many main-built asteroids that we've been looking at, thousands of Trojan asteroids that we've been looking at, starting to do rotation periods also from ZTO photometry now, and many, many comets. So for comets, in fact, we have this thing called TAILS, which uses deep learning to look for comets using just the reference image and the new image. So a lot of interesting things happening on that front as well. We've been building this field guide to do the classification for scope. I'm going to go past that. We have been doing a lot of Zooniverse initiatives for quirky transients, Taylor's Lewis and Chemical Factory. Also leave that apart right now as I'm getting close to the end of my time, and I'll leave you with this summary. So the alert stream that we have been producing has been feeding many brokers and classifiers. Bi-monthly data releases, lots and lots of data there for you to explore. And early detection and classification of transients is the key. Extensive classification using archival data and interpretability being woven into machine learning. I'll stop with that, and I'm happy to take a few questions. Thank you.
Okay, thank you, Ashish, very much. So, please, any questions?
Here.
Okay, just I will check the Zoom. Yes, you're only one, please.
Yes, I have two questions, Ashish. There is one, maybe I missed, but I remember that the number of alerts you provide per night or per day is enormous. So, for example, how many supernova type 1A do you produce per day or per night? That's the first question. Right. The second question is about the diagram of the example of RR that you showed. I think I saw already this, maybe I already asked you these questions, but it seems that there is no problem of classification of RR type C versus eclipsing binaries EW. Am I correct? So that's these two questions.
So what we have, let me answer the second question first. So what you saw there was the RR Lyrae classifier. This one, for instance, so as RR Lyrae objects they go into each of these classifiers. So every object going into each of these classifiers. So what that means is that for every object, we get a confidence value for each of these classifiers. So when you ask whether an object is one object or another, you do have those numbers for everything. Does that answer your question? Or was it something else that I missed there?
Yeah, that's maybe.
Okay, yeah, so we have numbers for everything for every object. But if you want specific examples, we can go about it offline and take a look at those, any specific ones. And then for the supernovae, as I mentioned, what we have is this is the rough distribution, and these are somewhat older numbers, but they are mostly scalable. So you can see that what we have is that supernovae type 1a is about 38% or so. And then the type 2 are about 46% in that set that we had. And you can go to higher numbers. And the total number of brighter than 18.5, we had about 3,700 as of last night in roughly 3 years. So it's of that order that you get about 1,000. So a few every night. And then about 1/3 of them are 1As. And then lots and lots are type 2s. And these are the rare ones that we are trying to classify better with the smaller samples.
Okay, thank you.
Okay, for more discussions, go to Slack, of course, and one more question from Łukasz.
I just have two quick ones.
I don't know.
Sorry, Chairperson. So the timeline, I mean, this is such a great experiment, the ZTF, and of course it has the heritage of IPTF and PTF, but now you're building, the ZTF is building heritage. There's a large group of people, there's a lot of expertise developing in amazing directions. So that would be a shame to stop it too early, but what's the cutoff date? Do you know about it? Because maybe I missed it, but this is something, we would like this to last as long as possible. So a comment on this would be useful. And another quick question is, have you found a comet already which has a ZTF name?
Yes, so there are comets that ZTF has found. I don't remember whether it has ZTF name because I think it has certain rules that they were using. But yes, we have found comets that ZTF has found. And then ZTF should continue. We are hoping that, so we have plans. We are going to put in proposals, and there are specific extensions that we have in mind. So we are hoping that after the ZTF2, there will be other things. There are also parallel things that are happening. Mansi is putting together Winter, for instance, which is going to feed into some of the ZTF things that we are doing, which should help with the next iteration of ZTF as well. So just like you, we hope that ZTF will continue.
Great, fantastic.
Okay, thank you very much. And the last one for today, and the longest one for today, Paweł Zieliński, how to use black hole Tom and CPCS. CS, sorry, it's too late for me. So, Paweł, please.
That's not my fault. I wish.
I saw you and I stuck. Sorry.
Okay, it's in full screen mode. So, hi everybody. Yeah, this talk will be the continuation of the talk presented yesterday by Maya. Maya did some nice introduction to black hole Tom. And I will continue with the same, but from the user perspective. So simply speaking, I would like to show you where to click, simply, to process your data, to use the black hole Tom, as well as Cambridge Photometric Calibration Server, which is closely related to black hole Tom, which is connected with this. So at first, if you want to go to black hole Tom, you must browse the link which is presented at the top of this slide. Then you will see the home page with where you can find, for example, the manual in the middle of the screen. The Black Hole Tom manual is presented. It will be updated soon because we recently implemented some features, new features. And on the right top corner, you see 2 buttons in green. Register and login. So login is simply for the users who are already registered, but if you are not registered, the first step is just creating an account. So by clicking the register button, this web page will appear, and you must provide the details and some word about yourself. If you are new to this, please write some words, because it is also helpful. It will help us to approve the account, because each registration must be approved by the admins, so simply by us. And you will be emailed when the account gets accepted. Please remember about marking the groups visible in the left bottom corner. These are the privileges you probably would like to have. Sometimes the users forgot about these privileges, but if you want to display, searching the list of targets, adding new targets, downloading images, uploading images, you must select all of these groups. So yeah, I encourage you to remember about that. Okay, and the main page in Black Hole Tom is presented here. This is the target list. So you must select the targets button to see the main target list with the targets projected on the sky. The red points are our targets. We have already 133 targets registered in Black Hole Tom. There is also position of the sun, position of the moon, and below there is the list of the targets with some coordinates and other details, which can be sorted by any of the columns. The default is the observing priority column. So the targets which are the most important at this moment are on the top of this list. And some of the users ask question about the observing priority, how it is calculated. So these are 2 examples for Gaia 19 CNM and Gaia 19 DUW. So the observing priority is calculated by using this simple formula. The last data point taken, dt, must be divided by the cadence required by the user. And all of this is multiplied by the priority. Priority is a subjective value, subjective by the user. It's a simply target importance. 10 means very high priority, so these targets are the most important for the users. 5 is a medium, 0 is zero importance. So these are actually not interesting targets for the observers, for the users. So here we have that for Gaia 19 CNM, the observing priority was calculated as 548. For Gaia 19 DUW, we got 12. So Gaia 19 CNM will be higher on the list. So we need data for this target actually. Okay, when you go at the bottom part of the main target list, you will see the space when you can filter the targets simply by putting the name of your target if you know the name, but also you can use right ascension and declination, sun separation, magnitudes. So this the targets can be filtered by in many different ways. So you don't have to go through the main list and look for the targets manually. If you click on the target, you will see the tiled page with many informations, with coordinates, with names in different catalogs, different surveys. And of course, there is also some classification comment. But there is also a series of buttons in the top. So simply by clicking photometry tab, you will see the photometric data, photometric light curve. Maya described this part yesterday, so I'm not going into details. Anyway, it is clear enough to know what is where, right? If you want to check for new data or to use this light curve in interactive mode. The second tab is for spectroscopic data. So if you have some spectroscopy done for your target, you can upload also spectrum, and you will see this spectrum in Black Hole DOM as well. But if there is no your target, you must create a new target, and you must create a new target page. Maya also presented how to do that from the scratch, but the simplest way is to use the catalog search option, the third one in this column. Then you will see a simple page when you must provide the name or part of the name of your target and choose the service, for example, Gaia Alerts or Simbat database. You want to look for your target and then add the target to your list. All of the data will be downloaded and presented in Black Hole DOM as well. So for the targets already registered in Black Hole DOM, you can upload the data. And you must use the third button, upload button, to browse and add your files and to add the data you wanted to upload to Black Hole DOM. Black Hole DOM supports ASCII files, FITS images, and CSV tables. So your data must be saved in one of these three formats. Please remember that the name presented here, Calypso server name, must be provided, because without that, the processing of Black Hole DOM it's not possible. So, first kind of data. When you want to upload some photometric results of your analysis, you did photometry and you would like to upload this data to Black Hole DOM to see it on the light curve, you can simply add an ASCII file, and then you must select the first entry, instrumental photometry file. But this file must be consisted of at least 4 columns, must be prepared in a well-known Sextractor format, source extractor format. These columns are the magnitudes, the uncertainty of the magnitude, and the coordinates, alpha and delta. The rest of the columns are ignored by Black Hole DOM, but these 4 must be provided. Then below of the same page, you will complete you must complete the details of observation. So you must provide the MJD date of observations, exposure time, and for example, you must select the observatory where the data were taken. That's also very important. And of course, there are other options. Matching radius is the radius which is necessary to compare your data uploaded to the black hole TOM with the catalog data. With so the catalogs must know the coordinates of your star, and the matching radius is just the arcseconds radius from the coordinates to search the catalog. Force filter is just for selecting the catalog filter to calibrate the data. Well, if you are new with this, I encourage you to leave it in auto mode as well as the default value for matching radius, just to check the processing results. And there is also nice to know that there is dry run option. When you mark it, no data will be stored in the database, so the processing will be done, and you will check the results, but no data will appear on the light curve. I always use it when I upload some observations for the first time or for new target. So when I use new instrument or when I create a new target and upload some data, it's always good to check the results before saving them in the database. So after completing these details and clicking upload, this data will be uploaded. The second option is uploading fits images. So the CCD images, after standard calibration, after bias subtraction, dark subtraction, and flat field normalization, can be also uploaded and processed by black hole TOM. You must then select the second entry, fits image for photometric processing. Then the processing will be done automatically by black hole TOM by using two tools, which I describe you later. And also you must complete some details, but this list is much shorter than before. You must just select the observatory where the data were taken, and the matching radius and force filter values must be provided. You can leave it in default as a default values. There is also dry run option, and by clicking the upload button, the data will be processed. And now it's time to go back to the slide presented by Łukasz a few days ago. When the observers have the fits images, so after a simple reduction, standard reduction, it can be uploaded to black hole TOM, and then black hole TOM uses two tools, CCD-FOT and CPCS. CCD-FOT will be described in details tomorrow. It is a tool also developed by us to do photometry and astrometry for every star in the field of view on the CCD image, identified in the CCD image. And CPCS stands for the calibration server. It's a tool developed by us for the calibration of the photometric data to standardize the magnitudes. So I will focus on these parts. Przemek Mikołajczyk will say more about CCD-FOT. This is a kernel of black hole TOM. This tool allows for automatic and fast photometric and astrometric solutions for each star detected on the image. The precision of photometric measurements is around 0.01 magnitude. The astrometric uncertainties are at the level of 0.01 arc seconds based on URAT, UCAC, USNO, and Gaia EDR3 catalogs, astrometric catalogs. CCD FOT can also standardize the FITS headers because it is important because when you have data from different telescopes and different instruments, you must know how to treat this data. And it can be also scripted to automatize the whole process of photometric and astrometric procedure. The calibration can be done and is done thanks to the connection between Black Hole Tom and Cambridge Photometric Calibration Server. We call it CPCS. It was developed primarily by Łukasz Wojciechowski and Sergei Koposov, and it can be found under this link, visible here. Some of you know this tool because it was used before Black Hole Tom. So we calibrate the data and create such nice light curves from many different telescopes instruments. To do that, you can also use CPCS tool without Black Hole Tom, but I encourage you to use it together with Black Hole Tom because it's I think it's more user friendly and much simple for the users. So here you have the example light curve for very recent Gaia 21 EFS event, which was calibrated to the one catalog, APAS catalog, in different filters, of course. These are data from several observatories, from several sites, observing sites. So as you see, the calibration is pretty nice. This is the results of the calibration done by CPCS. So after that, you will transform your instrumental magnitudes to the pseudo-absolute magnitudes based on the comparison with catalog data. So the calibration is done for many databases, many catalogs. Here on the right side, you see the list of the catalogs and filter bands supported in CPCS. So you can compare your instrumental photometry with all of these, or any of these in catalog and filter band. And you will get also the instrumental magnitude versus catalog magnitude plots, just to check the quality of your calibration. The best matching result is marked as red, in red. So you see that for this specific target, for this specific data, the best matching was done for APAS air band, and the 0-point correction equal minus 1.78 magnitude, which is written also, on the left side, is provided as well. So let's do some example. Let's imagine that we are all Josh Hams, and we have very nice telescope located in Chile. It's called RODE. It's 40 centimeter telescope, 40 centimeter, yeah. Located in Chile, in Atacama Desert. We got a nice image, and we would like to upload it in Black Hole Tom to put the new point on the light curve. Of course, it can be done after the calibration, after the standard reduction process. So we know how to flat fill this image, right? So we upload the image after flat filling. Then we must select the FITS image for photometric processing, the second entry, and select the observatory. So there is a RODE and the CCD camera mounted on this telescope already registered in Black Hole Tom. So I can simply select it and add it. Here, I leave it matching radius as a default. Also, I would like to check the results of the processing. The force filter is left in auto mode. So I will compare my data with all available catalogs and filter bands in this part of the sky. I mark dry run because I don't want to store this data in the database. This is just for testing, right? After clicking the upload button, you will see on the top the sentence that the data are successfully uploaded and our file is processing. This might take several minutes, but it's usually much shorter. It can take, well, maybe 1 minute and less. And it's good to refresh the page to check if it's done. But by using data button, you can see the uploaded data, and there are two buttons, all and your file. If you want to view the list of all data uploaded for this target, not only for us, but for also for other users, you must use this the all button. The your file button is for checking the details and removing the data of our files. So if you want to see the details or delete this data because we made a mistake, for example, we can do that only for our data. So let's go to see the details. By clicking the detail button, this web page will appear. On the left hand side, you can see the table with the results. It's actually the same result page as it was in CPCS. On the right hand side, you can see also the instrumental magnitude versus the catalog magnitudes plots. So these are the CPCS diagrams downloaded from them. So we know that our data were processed, were calibrated. We got the best matching plot marked in red. And we know that it was calibrated to the APAS catalog in B-band. And actually it is true because we did the observations in B-band, so it's fine. We calculated the absolute magnitude value, and we also have the 0 point correction. So we can view the results of the processing done by Black Hole Tom. Okay, we can also upload the CSV tables. So if we have data from another databases, like for example, like APSO, we must browse. We must use browse button and add the CSV file taken from them, and we must select the photometric time series. There is also the second photometric time series dedicated for assessing data. This is the example CSV table, which can be uploaded directly to Black Hole Tom. And you will see new points on the light curve. How to upload the spectrum? It's also very easy. Spectrum can be uploaded only in an ASCII format. So there must be simple text format with 2 columns, wavelength and flux. And you must select spectrum as ASCII. FITS format for spectra are not supported. For spectra is not supported yet, but we are thinking about that. Okay. But what to do if we want to create an observatory? We want to add our observatory to Black Hole Tom list and to be able to process our data from our observatory. Then in the top panel there is a button which is called Observatories. Then we will see the list of observatories which were added already in the Black Hole Tom, which are registered there. So by using all button, you check the list of all observatories registered already. If there is no your observatory, then you must add new observatory and must use this button. Then you will see a new form which must be filled in with the details of your observatory sites, longitude, latitudes, altitudes, as well as the technical details of your instrument must be provided, like gain, beaming, saturation level, and so on, pixel size of your camera. And it is necessary to upload sample fits image, which will help us a lot for finishing this process, because we must implement your observatory and your inputs to the black hole TOM. You will be emailed about the activation of your observatory, of your instrument. Then you will be able to upload the data. Some numbers about black hole TOM. It was used thanks to the Opticon time domain astronomy network of small and mid-sized telescopes, which delivered a lot of data. We were able to, thanks to them, we are able to use this tool and develop this tool. So at the moment, 73 users are registered. These are both professional and amateur observers, and 41 telescopes and instruments registered. On the right side, you can see the list of already registered telescopes. You can find yours if you are registered. And almost 2,000 fits images were processed already for 153 targets. Summarizing this, black hole TOM is a multi-user, multi-wavelength tool for automatic processing of time domain data. So you don't have to bother yourself about the data processing. It will be done automatically. I was skipping two issues. The observation request submission, which is also possible for three facilities: Las Cumbres Observatory, two telescopes, Gemini's telescopes located on the north and south hemisphere, and Liverpool telescopes. But this can be used only if you were awarded type allocation. Also, there is a possibility to do the steps which are described in automatic way, for example, by using Python scripts, and Przemek will tell you more about that tomorrow. And please remember that this tool is not finished yet, so it's not perfect for everything and everyone. The work is in progress, and we have a lot of features we want to add, we want to implement. We just started to from the most important features, right? So stay tuned, and if you have any questions, go to the website presented here, or just contact us by using Black Hole TOM mail address. Thank you very much.
Thank you, Paweł.
I will just add that apart from these means of contact, there is of course this Slack workspace, which is called Black Hole TOM, and the channel about this workshop is actually within that workspace. So if you have joined the invitation I sent you to join about this workshop, you're already on the Black Hole TOM workspace, and we can exchange, your feedback, your problems, your feature requests over there. I strongly encourage that.
Okay, Josh, you have the question, please.
Hi, Paweł. Thank you for your presentation, and thank you for mentioning my observatory, which I will present tomorrow. I mean, you mentioned that you are actually doing for all the stars in the field light curves. I mean, is it possible to get those light curves?
Yes, yes, sure. It's a short answer is that yes, it's possible. We just we just create the light curves only for the targets which are added to black hole photometry, which are interested for us. But if there is any other target interested in the same field of view, you can just download the fixed image and and add it in a next web page, right? Or by creating the light curve separately. But yeah, it's possible.
Okay, I will contact you by email.
This is a very interesting application of this, because we built this for individual targets follow-up, right? This is how it's all, that was the main kind of direction and idea. But as a side product, we of course generate light curves of thousands of stars which are nearby in the same field. So we have thousands of observations of the stars
which are hidden.
So they are there. They are in the database. But I don't think we didn't build any access yet to that. But the database is there, but we don't have it calibrated. That's the point. We have the instrumental photometry stored.
Yes.
But we don't have it calibrated. So this is something we've been thinking about, but this is not easily available. So if anyone is interested, we might actually give some priority to this, of course.
Yeah, but please contact us.
Yeah, cool.
Yes.
Thank you, Josh.
Okay, thank you. Marco, you have some additional questions, please?
Hi. Yeah, it's great to see Black Hole Tom mature in the last year and two. So I just want to see whether you can share any experience or comments on the difficult points, or whether it's very easy to integrate your interface with the Gemini and the Liverpool telescope, and also are they also using the Tom toolkit in order to talk to you?
Well, you can answer. So the Gemini and Liverpool, they were actually part of the original EON network, and they were kind of founders of this whole initiative of Tom at the LCO level. So actually, when you install a Tom from scratch from LCO, you get access, code which accesses LCO, Liverpool, Gemini, SOAR. These are all built in. And this is very fantastic. We've tried it and it works perfectly. Just 2 clicks of a button in the Tom and you get observations requests sent to Gemini. That's pretty cool. And the same applies to getting data from them. This is all built into Tom. And how to expand it to other telescopes is also doable. And the Tom group is very keen to help with that, and this is something what we are planning on doing soon, to add new telescopes to that list.
Okay, yeah, thank you.
Thank you very much. Okay, I don't see any more questions, or we have some? No, we don't have. Okay, so for today, I think it's everything. Thank you very much for attending this day.
Thank you, Monica, for chairing the session. Thank you to all the speakers today. And I remind you that there is this Gather Town link, and I hope that some people are using it. So we can meet there, but here, whoever isn't here in Crete, I think we'll go for some nice dinner now. Okay, thank you. I'm stopping everything here on Zoom.